इसमें कौन सा है कानून बहुत सब में गुजरना है last week the estimates are more
Respect, Honorable Vice Chancellor Sahab, Professor Hussain, Professor Philip, Professor Baljit Singh ji, and my colleagues and dear participants. This is the GIAN course sponsored by the Ministry of Human Resource Development. This course is given to only to the reputed universities which are having NAC A plus grade or above. And there is a very strong evaluation of the project of the course. And after that, this course is given to the university. This course was given before the Corona period, and we were struggling for revival of the course, and our Vice Chancellor Sahab has given us so much support for reviving this course and for making this course today up to this point, that we could organize this course, and the whole credit and support for this support, I'm deeply thankful to our VC Saabji for which is really unforgettable. He is such a scientific approach oriented person which I have never seen in my life. All support at any time is granted by him to uplift the department, to uplift the university. And from the chemistry department, we are deeply thankful to you, sir, for coming over to this course. So first of all, I will request Professor Baljit Singh ji to introduce the chemistry department.
Respected Vice Chancellor Sir, Professor Arvind, also introduced. In the year 1974, MSc in Forensic Science was also added in the list of courses run by the department. The Biochemistry Specialization and Forensic Science section have been developed into full-fledged and independent departments of biotechnology and forensic science, respectively. The Ministry of Environment, Government of India has recognized the Department of Chemistry as the Center for the Pollution Control and Environmental Analysis. At present, the department is offering organic, inorganic, and physical chemistry specialization to MSc students. The department has been awarded SAP DRS2 and FIST assistance established by UGC New Delhi and DST New Delhi, respectively. The department has a well-established instrumentation center equipped with the GCMS, CHNS analyzer, IR, UV, visible fluorescence spectrophotometer, and many other minor equipments. Apart from teaching assignments, the faculty of the department is engaged in many government and industrial sponsored major research projects and have many research papers to its credit. At present, nearly 50 students are enrolled in PhD program. It is an honor for our department that GIAN program is being connected in our department. My best wishes for the success of this program, and I hope our foreign guests will have a comfortable stay in this beautiful campus. Jai Hind.
Now I will request Professor Harsh to present Professor Hussain. And to Professor Philip. Now I request Professor Baljeet. Thank you.
In this course, Professor Hussain from the Deccan University, Geelong, Australia, is the main chief resource person. She is a full-time professor. Her scientific research is the development and application of miniaturized instrumentation across life sciences with a focus on portable and field deployable analytical instrumentation. Her research work ranges from fundamental instrument and chip design using computational fluid dynamics to the application of the microfluidic systems to point of care analysis, food safety, and bioprocess monitoring, as well as security, screening of explosive residues, and environmental monitoring. She also has an interest in the development of manufacturing methods for functionally integrated microfluidic devices, including injection molding and 3D printing. Her strength is in the building and leading teams to work together at the disciplinary interface. She has a very high impact over the last 5 years and more than about 200 articles published in Q1 journals. She is interested in strategies to enhance performance by focusing on deep learning and creativity. She leads a study implementing gratitude practice in RHD supervision with as result in enhanced productivity and reduced stress levels for students and supervisors. Besides this, we have another guest, Professor Philip Schmidt Coplin. He is from the Helmholtz Research Center, Munich. He is the director of the Research Institute, and it is a great pleasure. He is our friend. He is our um, guide of PhD students, and he is our postdoc father also. But more or less, he is just like a friend to us. We never felt like that we are in the company of such a big scientist. This is the greatness of Professor Philip. During this course, you will come not only to the lectures of these two distinguished personalities. Besides this, there is another there will be one lecture course by Professor Supreet, who is from IIT New Delhi, and our from our university, you will learn the 3D printing technology. 3D printing is a very advanced and future of the science, you can say. And if you can learn this technique at your childhood, this will be a silent aspect, or this will be a silent contribution to your career. And combination of this engineering, science, chemistry, physics, and instrumentations, all these are combined together and collected under this platform. I welcome you all and like to request Professor Arvind to say few words. This is all.
We can't afford to disturb the projector once again. All right. So, a very good morning to all of you. I'm very happy that the GIAN course is being organized at the chemistry department of this university. And we have a very distinguished professor from Australia, Professor Rosane, and we also have Professor Philip, who has been around with us for a while, and both of them will be participating and giving lectures in this course, along with others. Let me say a few things, because pleasantries are always fine. It's a good idea, great idea, all that we all know. I think many of you are research students, PhD scholars. See, what are our day-to-day activities when we do research? We measure, we read, we write, we plot, we analyze, all that and so on. Now, all this is done for a mediocre problem also, we have to do similar kind of work. For a good cutting-edge problem also, we have to do similar kind of work. So there is a principle that the motifs that you roll are not very different whether you are doing very interesting work or not so interesting work. Techniques, things are somewhat similar. Therefore, a lot of attention should be paid while choosing the research problems. And that's where GIAN comes in. The whole idea of the GIAN program is that we bring in people, we bring in collaborators, we bring in international visitors, so that we are exposed to fields in a way that we can choose more interesting, more important, more cutting-edge problems. My year and a half at Punjabi University, my main observation is that we are not choosing enough challenging problems and interesting problems which get attention to do our research on. We are looking research more as a way to get a degree or to publish. But publishing and getting a degree are benchmarks and landmarks just for bookkeeping. The real fun of research is to do something which is new, which is cutting edge, which you later on feel happy and proud about. That's one point I wanted to make. The second point I wanted to make was that don't get attached to techniques or equipment or ways of thinking, because you have to keep doing new things. And many times when new things are done, since we are a very old ancient culture, we kind of poo-poo and discard new things, and we say we are traditionalists. But when those traditions were created, they were very new. And any domain of knowledge which is expanding is always improvising, innovating, and reinventing itself. So we have such an old tradition of music in this country. But now in Indian classical music, on stage, you see harmonium. Harmonium is a Western instrument which came here in 13th or 14th century or 15th century. But the music is thousands of years old. But the traditionalists of Indian classical music accommodated and brought in harmonium, seeing its potential for that field. So this whole idea of getting too much attached to tradition is good, but getting attached to, because science is changing very fast. So you have to adapt and adopt what people are doing and move on that track. So these are some of the things which I think the GIAN program and the GIAN course can really help you. I would strongly recommend, along with the formal lectures, one or two informal sessions where people open up their mind, they talk about what research problems they're doing or thinking about, and some open discussion can happen where they can later on rethink and actually get something very concrete from the GIAN program. So the whole idea of GIAN is this: to come to the cutting edge, to learn what other people are doing, and to be able to innovate and perform at that level so that your research is relevant in the field. I always say that if you are into manufacturing, if you do little bit substandard manufacturing, it can still help. You are making bread. If the bread is 10% less baked, you can still eat it and get nutrition out of it. But research which is not up to the mark is completely useless because nobody really looks at it. So whatever you do, the quality and its relevance within the field should be an important thing for you. And I'm very happy that very distinguished scientists have agreed to come, which also means that our local groups are active and collaborating and doing well in this department. I really welcome you all once again on this cold morning beginning, but I hope the atmosphere in the room will warm up once the lecture begins. Thank you.
Thank you, sir. And at the last, I will request Professor Hussain before the start of the lectures to say a few words. How she feels here.
Thank you very much for coming. It's a great honor to be here and be talking with you through some of the achievements in the field of microfluidics in the coming weeks. I'd like to thank Professor Ashman for having done all the legwork organizing the GIAN to realize this before 2020 and then trying to do it online in 21 and finally being able to do very early 23. See you face to face because I much enjoyed being here. Teaching is great fun, but you get a lot more interaction being in the room. To the people that watch online, you've got my email address. So if you've got any questions or would like to be involved in the conversation, you're welcome to do that as well. And I'd like to acknowledge the university as well, so chemistry department for hosting me, putting me up here on campus, and I hope we'll have a great time together. Thank you.
We can, that's all for our inauguration, and we can.
So computers.
All right, good. So have a good time. And how many days you're here?
Till Friday.
So feel free to come for a chat or a cup of tea to my office. Maybe this is more than half hour so that I can get some feedback from you also.
Yeah.
Okay.
Okay. Thank you.
In the meantime, we make all this arrangement. All the participants can have a cup of tea in 15 minutes. Okay? Everything is ready. तो किसी भी तक का बोल
कोई देखा क्या आगे कुछ नहीं फर्स्ट देख लिया तो हमारा प्रोजेक्ट भी बनता है थोड़ा पीछे यहाँ फ्लो चल
किसका बता?
As per the conditions, we are transmitting this online also.
Yeah.
I request all the participants that I have mailed you the schedule of the course. Please be in time and because we are on the other internet also. And this program is live streaming. And if you have any question, any doubt, you are free to ask Professor Hossein or the other dignitary who is delivering the lecture. And please feel free, feel at home, and if you have any questions, you are free to reach any type of problem. Now it is between you and Professor Hossein for the rest of the day. Like it is your, it is our privilege that he is here, and if we can introduce each other, you are, can you tell your name and from where you are?
I am I am a student of Master in Environment. I am a student of Master in Environment.
Yeah. Since practicing.
Both resolution.
resolution that come in. और लाइट भी पूरी बंद कर दी गूगल मीट कितने के कैमरा कितने डिस्प्ले हो रहा है अच्छा वो जो गूगल मीट चलेगा वो तो कैमरा डिस्प्ले होगा कैमरा चल रहा है कितने शो नहीं हो रहा है इधर शो हो जाएगा आवाज आती है आवाज जाएगी प्रेजेंटेशन जाएगी ਹੁਣ ਆਪਾਂ प्रेजेंटेशन बाहर करती है फोटो नहीं जाएगी फोटो नहीं जाएगी थोड़ा टाइम प्रेजेंटेशन बात करें वो तो करने से इंटायर स्क्रीन शेयर नहीं विंडो कर लेती है टॉप सेटिंग से आज बंद हो जाएगी तो गूगल मीट को टैब ਵਿੱਚ पर्टिकुलर टैब ਜਿਹੜਾ ਹੈ ਸਿਲੈਕਟ ਜਿਹੜੀ ਪਹਿਲਾਂ ਓਪਨ ਕਰ ਲੈਣੀ ਫਿਰ ਸ਼ੇਅਰ ਕਰਨੀ ਪਹਿਲਾਂ ਪ੍ਰੈਜੈਂਟੇਸ਼ਨ ਓਪਨ ਕਰ ਲੈਣੀ ਫਿਰ ਸ਼ੇਅਰ ਕਰਨੀ तो फोटो नहीं आएगी जब मैं स्टॉप शेयर करूँगा फोटो आ जाएगी
So thank you very much for at least getting me an idea. I had it planned somewhere in the middle of the slides. You'll find one that says, please introduce yourself, but we've done that now. So it's great to know what we've got here and the great diversity of participants we've got. And I'm really excited to just have fun in the coming 2 weeks talking about what has been going on in microfluidics, but I think we should more so have a look to see with the expertise here in the room, if we can come up with any ideas on how to progress the field. Because listening around, we're going from pharmaceutical science, a lot of organic synthesis I've heard, biotechnology, engineering, physics. We've got a lot of different expertise in the room, and that's what I hoped for, and why it's also been fairly challenging to prepare the lecture notes, because you all will have very different backgrounds and knowledge in different areas. My name is Rosanne Guit. Guit is a Dutch name. I'm originally Dutch. And outside the borders of the country, no one can pronounce my surname, which is why everybody just calls me Rosanne, which is the Dutch way of saying it, or just Rose. I'll listen to all of them. So just call me Rose. And if during the lectures you've got any questions, you want to discuss something, please yell out. We're here to try to learn and progress the field together. I have prepared a whole range of materials. If you've got any things you want me to add on, if I've got the time, I'll do it, and we'll change some things. So there's a lot going on, as you'll see, and there's a lot of different angles we can take on the field of microfluidics. In addition to this introduction round, I'll start off today with explaining you a little bit of my background, because it overlaps with a fair few of you, and it means that as scientists, we're not actually sitting in a single box. So I'll give you a little bit of an idea of the different things I've done. And then I thought it was nice to also give you some background on the part that kickstarted the whole microfluidics research, which was the miniaturized analysis system introduced by Andreas Mans in 1989. So for those of you with a pharmacy background, we're in good company. I did my undergrad in biopharmaceutical sciences at Leiden University in the Netherlands. So that's a pharmacy degree to do research in pharmacy and not necessarily to become a pharmacist. So I can't do the prescription, I can't deal with patients, but I got trained a whole range of different things about the synthesis and analysis of pharmaceuticals. As part of my undergrad studies, I specialized in analytical chemistry, where I did a project combining capillary electrophoresis with mass spectrometry, and because we needed to remove some uncomplex antibodies, we had to do that through the collection of free flow freezer cell. It's come back a couple of times after that in my research life, and we'll have a section as well about free flow electrophoresis. So rather than killing rats and mice as my fellow students did as their final projects, I went analytical and have great fun doing some wire imprinting to do very early budget microfabrication, which is a research line I've continued since then. I've then, since I've completed my study, spending a couple of months at Technologie Servier in France, trying to install capillary electrophoresis there as a method for counter-ion analysis. After which I not sure why one of them is there, blue there. I started my PhD and I then went to a technical university. So that's Delft University of Technology, which isn't that far in the Netherlands from Leiden. And I did my PhD there between biotechnology and electrical engineering, which is where I had to learn to speak a little bit about engineering. The electrical engineering part was mainly doing clean room processes as well as the understanding of contactless connectivity detection. My little bit of fame, or the glory of my PhD, was that I was the first one integrating electrodes for connectivity detection in a capillary electrophoresis microchip. So we, working with the electrical engineers, we made microfluidic devices in a couple of different ways out of insulators so that we could do capillary electrophoresis in there. But we put metal electrodes there that were initially in contact with the solution to do conductivity detection of the analytes coming by. And a little bit later, we put an insulator on top of those electrodes in order to do contactless conductivity detection. After my PhD, I moved to Australia. So that's where the confusion comes from. Am I Dutch or am I not Dutch? I got a scholarship to work, to start a lab on the chip research at the University of Tasmania in 2003. And then that got followed up by a fellowship. So I stayed in the School of Chemistry at the University of Tasmania between 2003 and 2010. After which I moved my office by 50 meters to then become part of the School of Pharmacy, which then got merged with the School of Medicine. Not really changing my research, but taking on some teaching of pharmacology. After that, I got a von Humboldt Fellowship, which is where I also met Professor Malik. I got a fellowship for 2 years, which I split into 2 parts. What I haven't told yet about is my personal situation. So I'm married and I've got 3 children. Took the 3 children from Australia to Germany to live for a year. Then thought it was a great idea to get back to Australia for a year with all 5 of us, to go back to Germany for a year with all 5 of us, to go back to Australia. So we've done a little bit of flying around with the family. Kids are portable, is what I learned there. Kids are really adaptable. And we had a great time. So the first year was at KISS Europe, where I had the absolute honor of sharing an office for over a year with Professor Andreas Mans, who started lab on chip research. And that was a really interesting time, just having an everyday chat and see how a mind like his, how it actually works. The second part of it, I decided to get a little bit of an idea on how the industrial part of microfluidics works. So I was actually placed at the microfluidic chip shop, which is somewhere else in Germany. And again, had a great time there, realizing how hard it is to upscale production and manufacture the devices so that people can actually buy them as an off-the-shelf product. What was great, however, at the microfluidic chip shop, that they're a chip shop, they're a shop. So you go shopping and you want one of those devices and one of those devices, and there's just shelves and packets full of designs, and you can just literally get them off the shelf. They're a shop. And as someone that's come from a long time research period in microfluidics, where every great idea you have hits the first barrier, how we're going to make the bloody thing, it is actually really, really nice to be in a shop and just get a design off the shelf. It's sealed, it's working, it's cleaned, and you can work with it. So that was a great year as well. While in the chip shop, I got a job offer at GIAN University as a professor. So instead of the idea of moving back to Tasmania to reunite the kids with their friends, we spent 5 days in Tasmania before we moved to Deakin, which is on the Australian mainland. And what I do there is that I've got a research group developing new technologies for the early detection of threats and disease in the Center for Regional and Rural Futures. Having worked in a School of Chemistry, Department of Mechatronics, School of Pharmacy, School of Medicine, and now in a center, my research actually hasn't changed. And I think that says it all for what the field of microfluidics is about. It's a toolkit, and typically you've got design elements, fabrication elements, and application elements. And it fits kind of in all different disciplines in schools. And I think the backgrounds that all of you have here reflect that as well. So I did a Wordle a little while ago on what my publications are about, get you a little bit of an idea of what I've been doing. And based on, yeah, I'm happily talking to what I can see on the screen, but you're not watching along. That's not good. Why are we not? Why does my computer say it's in presenter mode and not go with you? It looks like only the online people can actually see the slides and you can't. Sorry about that, you should have spoken up.
I don't know why it is not showing here.
Did you put that now?
That's the code.
Yep. So that's Surf at the moment. And that's a Wordle. So a lot of my articles typically have in there making microfluidic devices for something. I've done a fair bit on detection, so you can see detection in here, contactless conductivity detection, detection electrodes, instrumentation, played out a little bit in the area of polymer electrodes and finding ways of machining them to move away from all the problems and the costs involved in metal electrodes integration. But organic there. I also did some work on microreactors. I was overwhelmed by the amount of organic sensors here. I haven't done a lot of organic chemistry, but I have had a project where we created a polymer monolith for heterogeneous catalysis. So the polymer monolith that's normally used in separation science, we put a catalyst on top and did flow through catalysis through that. So that's been my little research stint in organic synthesis. So I've just spoken with all of you, and please forgive me if I don't remember your names. I'm really bad remembering names at a good day. 20 names in one circle around is not going to work. So you probably now have heard my name a couple of times. Please forgive me if I don't remember your name if you come up to me. What I'm really curious about, and also to just tailor the content for the coming 2 weeks, because we'll be spending a lot of time together. Is there anything particular you'd want to know about? And if you, for the people online as well, I'm not sure if we can come in through the audio, but my email address is Roseanne, my first name, @deakin.edu.au. Please feel free to send me an email if there's a particular topic you'd like me to include or add some information about. Maybe it's already in there, maybe not, but please speak up. I'm happy to be flexible and then change some of the content around to better suit any of your needs. Anything on your mind yet? Not yet? Then, yeah. Let me know if there's something that really interests you through the course. We'll be having snippets of a lot of things, microfluidic. The only thing that we won't be touching on is any cell culture stuff. The field of microfluidics has moved to realize that microfluidic channels are actually ideally sized as well to control and culture cells. That's a whole field in itself. It's not where I'm really comfortable with talking about because I have not done a lot of cell culture myself. We've done some really cool stuff with neurons. So if we've got people here that are interested in cells, I'm quite happy to throw some content in there about how we have been guiding the exons coming off a neuron through a maze so that they get lost and the glia didn't. So we've done some really cool fun and games with neurons. So any people that are into cells? No one likes cells here. All people that only like molecules. We've got someone, okay, we'll put our exon maze in there. It's just been submitted after 4 years of waiting a student to get out parental leave. I need to see what slide, but yeah, we'll throw them in. As all things in the whole world, everything starts with money. Unfortunately, before we can do a fun research project, we need to get funding. And some people in life are luckier to get funding than others. And Andreas was one of the, Andreas Mans, the starter of the field of microfluidics. Are we going backwards? So Andreas Mans, one of the people was in a very lucky position, being at the right place at the right time. And some of the slides later talk about there was big environmental in Switzerland. The public got really about all the environmental damage being done. There was a whole range of fish being dead, floating around just past Basel. And as a result, the pharmaceutical industry decided they need to do something different and get a much better chemical monitoring system out into the environment to actually quickly pick up whenever there had been an accidental release of chemicals from the pharmaceutical industry. And by picking up that earlier, mitigates the death of fish and then don't have the environmental impact so widespread before anyone picks it up. And I hope we have sound and audio because Andreas got a really nice movie being made about the field of microfluidics when he became a European inventor. And
just a tiny prick, but
hope
it
that we
can
can have the audio here.
This is made possible using special
Do we
test
not have
equipment.
speakers on this computer?
Such a process is called lab on a chip. It works like this. Within seconds, the system analyzes blood samples and then gives a reading of the blood sugar level.
The concept was pretty much inspired on
The ability to replace a complete laboratory with rapid tests such as these is the dream of many researchers. Andreas Manz's pioneering invention is a big step in this direction.
Multi-channel capillary electrophoresis.
The chemist has shrunk the lab to the size of a chip.
Where you can put different samples in.
I was one of the first to employ microchip technology in the field of chemistry,
Different parts of the
and
chip
to have shrunk the laboratory to the size of a chip.
And then one after another, the assembly.
Today, Mans teaches at the Korean Institute of Science and Technology in Saarbrücken. Here, he can pass his wealth of experience on to his students.
A slab gel electrophoresis.
His world-famous mini chip was conceived in the 1980s.
So that's
Working on behalf of a pharmaceutical company at that time, Mans was able to take all the functions of an entire laboratory and put them onto a single chip.
So I'll send you around the link to the movie is actually quite
What was
nice,
new
talking
was that
about
we integrated equipment, hoses and valves from the laboratories into tiny tubules on a chip.
Much better said in Andreas' word than in how I could do
And
it.
this method allowed
So I'll
us to
get you
bring the
links so you can
device
watch
to
the
go,
movie.
so to speak.
So he was
A
European
lab in your
inventor
pocket,
of the
which is
world.
cheaper and much faster.
The year in, I think it was 2015.
The mini
And it
lab
is on
works like
the,
this. On the chip,
this
there are
movie
tiny
they made
channels
on
and
that
depressions
occasion.
for the flow of liquids. So, for example, if a drop of blood is applied, blood
So it all started in 1986 when there was a great environmental disaster in Basel. And I particularly like this picture that one of the newspaper drew. You're probably not that familiar with the map of Europe, but Basel sits kind of here. So there's the Alps where all the melting snow water comes down and the river goes through Basel, Freiburg, and then goes into the North Sea. Basel has got a huge amount of pharmaceutical industry, and 2 times in a very short period, in 6 times in a row, they had a huge chemical spill. One of them was pesticides, I think the other one was something else. Yeah, they had a fire in a factory, and that pretty much killed everything alive and swimming in the Rhine for hundreds of kilometers away. And as you can see, the people were absolutely not impressed with the amount of damage that the pharmaceutical industry did. As a result, Andreas came up with the idea of the miniaturized total chemical analysis system. It took a little bit, so in 86 the disaster happened, so in 87, 88 the funding became available. Andreas was luckily working as an analytical chemist in a pharmaceutical lab and found himself all of a sudden sitting with a lot of funding and a very big environmental problem and a need that something else needed to be done about environmental monitoring. I have asked you to change. So he came up after doing a research stay in Japan, where he had been in touch with a lot of microfabrication, came up with the idea, why don't we do chemical analysis, but then on a microchip? And we call it a miniaturized total analysis system. And it works pretty much like an ideal sensor, like we know from a glucose sensor, a pH meter. You poke the sensing element into the water, and you get a reading. But the difference of this sensor is that it actually does all the different steps of a total chemical analysis system, all integrated. So we're not relying on an ion-sensitive membrane to only sense one analyte at a time. We have the ability to have the complete workflow from sample pre-treatment, the sensor itself, which could be a selective or non-selective detector, and the electronics recorder, to have that all integrated in a system. And if you overlap this one with that one, so you've got an ideal sensor, like the pH meter, and a total analysis system which combines sample treatment, separation, and detection. If you put them together in one box, you end up with a miniaturized total analysis system. And there's a couple of advantages for doing that. Initially, the obvious one seems to be that you might get smaller. But that was not the absolute drive. The drive is that if you miniaturize analytical chemistry, life actually gets better, or at least the analytical performance gets better. We've got less problems with diffusion. So if we miniaturize the analytical system, we get better performance, and we get a whole range of different additional benefits. But the molecular diffusion, heat transfer, and the flow characteristics, they are the ones that determine the band rolling. And I don't know if it's Professor who was teaching the chromatography. Not you, is it? No, you did the electrophoresis. So we will be talking about chromatography tomorrow. And the big fear of chromatography is band rolling, where the peaks wider because of diffusion. If you miniaturize your separation, you can make your time shorter, which means you have less diffusion and much narrower peaks. And if you don't, all the time-related variables, so the time that you need to wait for your analyte to interact with the stationary phase, the time that you need in an immunoassay to have your antigen find your antibody, all those times scale not by a factor 10, but by a factor 100. So they scale to the square of the size of the system. So you can actually make significant by miniaturizing the system significantly down. Probably for those playing chromatography is that pressure increase with the square of the system as well. So pressure-driven systems, pressure-driven separations are probably not as well off, and that's why there's a couple of us in the room here that like their electrophoretic separations, because all you need is an electric field, and you don't need to push liquids through very small channels. Later, they will go through a little bit more physics there, but the smaller the hole, the harder it is to push something through. A lot of the physics in microfluidics is actually, you may not realize it first thing up, but there's a lot of common sense there. It's harder to push liquid through a small hole than through a big hole. So it's harder to pump liquid through a small channel than it is through a big channel. The miniaturized analysis system, there's always people that have similar ideas around similar. And whilst the microtest got some traction, there was some actually in the US as well, where they didn't talk about the microtest system, but about the lab on a chip and shrinking the lab down to a chip. And those systems have kind of started to exist. The terms have started to merge and blend and be used all the way through. So the miniaturized total analysis system is mainly a term used by the more traditional analytical chemists. A lab on a chip is fundamentally a lot broader because it also includes non-analytical processes like microreactors, like cell culture systems. But with time, where the terms come from don't really matter anymore, and microfluidics and lab on a chip are now just synonyms for the same thing, doing chemistry-like stuff in small channels. There's a whole range of other advantages that you get when you miniaturize down an analytical system. First one is that you reduce the consumption of the sample and reagents. That's great. The sample volume, for example, you do analysis on newborn babies, you don't have 50 milliliters of blood to get out of them. So having an analytical system that doesn't need huge sample volumes is really great if you're limited in number of sample in the sample volume that you can deal with. Limiting the amount of reagents is always good, even if it's just from an organic perspective. Most chemical reagents are not great when they're expensive and not great when released in large amounts in the environment. So if you can minimize your reagents and solvent use, that's always good for the bill of the project at the end. You get a faster analysis speed, and we'll go through a fair number of examples showing you how fast you can actually do a chemical separation on a microchip by reducing down those dimensions. By having less time, more integration, less reagents, the cost per analysis can be significantly reduced. And that's a great advantage if we want to go to monitoring. Because one of the things that sets the original idea of the microtest apart from the lab on a chip is that it had autonomous sampling. And therefore you can run a lot of different analysis at this, sequentially, and you get insight in time-based events. Cost is one of the biggest reasons that we don't have great insight in temporal changes in a lot of chemistries around us. We may measure the chemistry in a lake every week or every month, but we don't get a sample taken every minute to understand how actually at a small scale chemical profiles in the environment or in our bodies, how they change. And the big reason for that is cost, because it is very expensive to have someone driving to the lake every minute to take a sample and then shuttle it back to a lab for analysis. So being able to do that all on site is very important, but it needs to be affordable as well. So that's great. With being a smaller instruments requiring smaller volumes, it means that we get a lot more deployable, which means that we don't need to have analysts driving up and down to the lake anymore to get a sample and get it analyzed, but we can do on-site analysis, which is something that we, in diagnostics, it's the popular term point of care diagnostics. For more environmental, we use the term point of need analysis, which is a little bit broader, and it also covers the lakeside or riverside testing. We've got a much increased level of integration and automation. And in a little bit, I'll talk about how small actually is and how little of volume you actually have in a cubic micrometer. It becomes really hard to handle. A lot of you will be quite competent dealing with milliliters, low microliters. It's always a pain because you need to calibrate those autopipettes. If we go smaller than a microliter, life gets really, really hard in the lab. And that's why we need our microfluidic tools to deal with those small volumes. The great thing is we can actually automate them, so we don't need to fill 24 or 48 tubes with the same reagents. We can just get a fluidic algorithm to do that all in one go for us. Smaller also means lower power consumption. Again, one of the projects I'm involved in is for environmental monitoring, where we've got a solar powered system to autonomously take water samples and analyze them in 1 hour. we want to be able, even though it's solar powered, we want that system to be able to also sample on a cloudy day. So we want all the processes to take very little power, and we can do that because our analysis time are only very short, using small volumes, so we don't need to pump for very long times. We don't need very high pressure because in this instance, we use capillary electrophoresis for the separation. Reduced risk is another very, probably more relevant for the organic chemist in here. If you've got a highly exothermic reaction going on in the lab at a scale of 50 milliliters, things can actually get seriously out of hand. The bigger the scale, the bigger the consequences if something goes wrong. If you've got a highly exothermic reaction taking place at the microliter volume, you may have a crack in your chip, but that's probably as bad as life gets. So you can actually do much more dangerous chemistry when you package it in a small microchannel, because on the human scale, even if we get an explosion or we get a lot of heat being generated, I've seen sparks on chips. Sometimes something goes wrong with the electric fields, but it's never been intense enough to actually cause a fire in the lab. Making an agarose gel for gel electrophoresis is probably the biggest risk. Dissolving your chemistry is more risky than doing any of your processes on the chips. So if you want to do highly exothermic reaction, there's actually a great advantage in downscaling because your risk is a lot smaller than it would have been when you do it on a small scale. And we now can get to the slide that I've been wanting to jump up for a very long time. How small is small? And in microfluidics, we're kind of flexible with the terms. There's a whole range of definitions out there. Initially, it was things that are tens of micrometers. Then channels started creeping up to be under 500 micron. Then the term millifluidics came up for plus over a millimeter. So if we take it kind of broad here, we can see the microfluidics at scales that are at least one of the dimensions is smaller than a millimeter. So we can have a channel that is 10 millimeters long, but then it may be 200 by 500 micron in dimensions. And then that's a large microfluidic device. And then it goes all the way to the small channels that are 5 by 5 micron. I think and then we won't be touching a lot on the nanofluidics, which are then the channels that are nanometers in size. So there's a whole world out there as well, which have got very different challenges, including how do you image on the microscope. But if we look at the volumes that are involved, we actually scale really, really rapidly in volumes. So if we talk about a normal analysis system where everything is in the size of millimeters, then we're dealing typically with microliter volumes. If we go down to the systems that are hundreds of micrometer big, we actually go to volumes that are nanoliters to picoliters, which is, we can quite easily visualize how much a milliliter is. If you've done a lot of biochemical work, worked a lot of micropipettes, visualizing 10 microliters, 20 microliters is easy. Visualizing 1 microliter, well, it's kind of 10% of that plug that you know that is in the little yellow or white pipette tips, the 10 microliters. And nanoliter becomes really, really hard to figure out because if you've got it sitting somewhere on the surface, it's evaporated before your eyes can actually focus. And if we then start talking about the small micron channels, we start talking about even smaller volumes. It is nice to have some correlation on how big things are. And in microfluidics, the microchannels typically have the dimensions of a human hair. Range from the very thin hairs for the small microchannels to the thicker hairs. I think Asian hair may be the thickest, being around 200, 250 microns. So human hairs, depends a little bit where they are, but microfluidic channels, typically the dimension you're talking about are a hair, and then you do chemistry inside a hair. So hard to handle fluids on that dimension. You can see them under a microscope if you're lucky, but seeing it with a bare eye is impossible, and that's why you need to trust your physics to work, understand your hydrodynamic resistances, because otherwise it's really hard to confirm your chemistry is doing what you think it should be doing. If you're working with 10 milliliter test tubes, you can see what's going on and you can kind of double check yourself. if you're doing it on the micrometer scale, nanoliter volumes, you need to just have a very good idea what fluid is where, because unless they're really dark blue in a lot of microchannels under big magnification, most solutions look transparent, seeing color differences. Despite all the beautiful pictures I've got throughout all my presentations, seeing color in microfluidic devices is really hard. You need really, really highly concentrated food dyes to be able to see what's going on, because a lot of you will have done UV spectroscopy. Lambert Beer path length is a part of the amount of absorption. If you reduce that path length to 50 or 20 micron, you don't have a lot of absorption left. So your poor eye is really struggling to see any color changes. And that's one of the reasons that a lot of people use fluorescence microscopes rather than transmission microscopes looking at microfluidic systems, because color is really hard to see unless you've got really intense dark blues. With small volumes comes another challenge that is as an analytical chemist, because as an analytical chemist, we like to detect molecules. One of the problems is that the molecules need to be there. So if we go for very small volumes, we actually do still need to reassure that there's a couple of molecules that we're interested in are in our sample volume, which is something I'd never thought about up to the point I saw the figures there. But indeed, if you go to very small volumes, very small concentrations, it becomes kind of a lottery if you've got your target analyte in your sample or not. Here on the 90s, people already made a nice plot of it, where the line here, you can see the sample volumes in liter and the number of copies present in that solution per milliliter. And of course, there's a linear cutoff. There is a point where you can't be guaranteed that there's a single copy of your analyte in your sample volume anymore. And that's important to keep in mind, because we can develop beautiful microfluidic systems. But if we're talking about low volume targets, we probably need to come up with a way of concentrating those targets into a small volume that we introduce into our chip for analysis, because otherwise we risk running an analytical assay on a sample that doesn't contain any of our analyte, whereas in the larger sample that analyte was present. So if you're developing an analytical system that needs to be really sensitive, please do the maths every now and then on how many molecules you actually have per microliter and per nanoliter. And if you're not accidentally ending up in a range where your sample that you want to inject into your analytical system contains less than a molecule per sample, because that's, you start looking for the needle in the haystack. There's ways around that as well. So we'll be talking about the digital PCR, but there's a whole range of coulometric reactions as well, where people use small droplets as small individual containers to do individual reactions in. And just rather than measuring the average color of a 500 microliter volume, to make it understandable what we're looking at, you look at the number of colored droplets versus the number of non-colored droplets to get an idea of concentration. So you count 50,000 droplets and you see how many of them had an analyte in there. And then you can get back to concentration as well. So if you only have very few targets in your sample, either you need to concentrate it to make sure you remove water and therefore still have your sample in the target volume that you're injecting, or you need to come up with a different strategy and the digital PCR. And after that, a whole range of other digital analytical techniques have been introduced, where it pretty much per very small container, your analytical assay becomes a yes/no answer, and you can then say later on, so many percent of my droplets were yes, and therefore concentration of my original sample is so much. But it works as well. One of the great things, and how many of you have actually played with a microfluidic system in the lab? No, fun and joy. You get this lovely, beautiful chip, and if we go towards 3D printing, I'll bring some in. There's a couple of them in my suitcase. You end up with this beautiful microfluidic device in your hands, and then you're like, how are we ever going to get a solution in there? How are we going to connect the pump? And if you look at literature, there's a whole range of different ways that you can do it. And this one shows nice blocks. So you can see here on the right-hand side, you can see a block where different kinds of flexible tubing are being put in place. And this chip has been designed to nicely fit into this block. You can just click them together like Lego. So you need to invest some time in engineering to make a fluidic interface like that. Having lost a lot of time trying to hold the tube in place and super glue the tubing on the glass and hope that you hold it still enough for long enough and that the glue doesn't make into your channel and destroys your chip. Actually, having a connector is really, really good. And designing your chips, maybe your channels are a bit longer or in a different position, but designing your chip so that it fits a fluidic connector that you can buy. Alflow's got some Black House Collective. So there's a fair few microfluidic connectors that you can buy these days. Having a way to interface, or we'll go to 3D printing. 3D printing is great because you can actually buy or print the female version of the upchurch fittings. You can print them with it. So your chip comes out of your printer and you can just plumb your pumps to it because the fitting is already part of the chip. Really great thing about 3D printing. And if you ever venture into the area of microfluidics and you're there with your super glue trying to get the tubing to stick because you want to connect your syringe pump, connectors are a really good thing. And you can see another kind of connector sitting here on the other end. So the connector that we see here on the right plugs in like a Lego block. I hope we've all played with Lego as a kid. This one here sits on the flat end, so on the flat end of the microchip, and slides over that part. So there's different applications where you would like to have different inlets and outlets. There's connectors commercially available for both systems. If there's nothing available, talk with a good mechanical engineer. I think we had our engineering group. Physics and engineering here? Were you an engineer? Yeah, we've got an engineer in the room. They're really good making holes, and interfacing your chip with fluidics is really important. So make sure, if you don't think you can devise something up yourself, make sure you talk with an engineer, because life in the lab can be made a lot easier with a couple of good engineering solutions. Talking a little bit more about microfluidics from an engineering perspective. It is all kind of a network, and that's also the best way to start thinking about microfluidic systems. We've got the, probably all had some basic electronics or physics done with resistors and voltages and currents, Ohm's law. Hopefully all crossed your path at one point in time, that you can have resistors in parallel and in series, and you can add them up, and you do that different ways depending on their parallel series. The lovely thing is fluids work exactly the same way. So you can consider a fluidic network as an electronic network, where every part of your microfluidic system becomes a function of, it's an electronic resistor, flow resistor, your flux, your flow becomes, your current is equivalent to your flow, your pressure drop becomes the equivalent of your potential difference. So a lot of the analogies of electronic circuits actually directly translate to microfluidic circuits. And the same methods apply, the same way you can deal with your flow resistances. Why that is important is that sometimes you want to balance your flows. And at that point, it is important that your, so a liquid has got the nasty property that it always wants to go the path of the lowest flow resistance. So if one of your channels is a bit shorter than the other, it's got a smaller flow resistance, and all your liquid preferentially goes that way, you never get a nice and equal split. So balancing your channels, having your channels of similar dimensions, or maybe you want to engineer a 2-in-1 split. You can very easily do that by changing the width or the length of your microchannel, and your liquid will just distribute itself as if it's an electronic network. Current and liquid flow do exactly the same thing, and keeping that in mind whenever you're designing device is really, really handy. Also, if you're second guessing yourself on my flow was supposed to go there, but it didn't, try to figure out what's going on. A lot of the fluid dynamics, it's very basic, but if siphoning is a big threat to whatever is going on, because if you've got your microfluidic channel and you've got two reservoirs sitting at either end, one is filled to the rim with liquid, the other one is empty, we've got a pressure drop. And our flows will go up to the point our pressure gradient is level. So if we don't fill our microfluidic channels, don't balance our reservoirs to the same level, fluid dynamics will do it for us. And in the period that's fighting its way to get to the same levels, none of your planned things will be happening because they first want to have equal levels, equalize the pressure. There are a couple of tricks that you can play with to stop the impact of siphoning. Any ideas how you could stop that problem of siphoning? Chemists in the room, physical chemists, we have physical chemists here.
The pressure from the other side.
Yeah, but how could, so if your levels, for example, your chemical process has got a small flow component, so through your test, your liquid levels are changing. How could you increase the flow resistance in a microchannel without changing its geometry?
Reverse osmosis, like
Viscosity. So you can add a polymer. If you add some hydroxypropyl cellulose, it still gets easy enough to just inject into a microchannel, but it gets a lot harder for these flows to really system where fast in there as some polymer. It doesn't do anything to your chemistry, but it increases your viscosity. It makes it a whole lot easier. It all is resistant, and resistance are relative. If you know your resistors really big, that tiny pressure difference doesn't make a difference anymore. It's one stumble across 25. So we've got an electrical circuit is similar to the flow in microfluidic structure. In microfluidics, that's a very important lesson to learn that helps in analyzing a lot of troubleshooting. It's not a lot of textbooks. It's one of the things that work in the lab to either design or to and your research change and nothing. So yeah, if something, look for errors there. So markets are very big. The structure of constructs that we got a little bit of to get through that. But we'll go for some of the fluid dynamics. We'll then touch with some again in optics of detection and the electronics in sports. System to work. Find someone still to learn the tricks of the trade and how to design it. All this will go if you want to
Share this and slide it. Where do you want to share?
Yes, no, where is it? Well, I just opened it.
This one.
No, 1.2. So that's that's the introduction. That's the wrong one. Or should I open it in the browser rather than in PowerPoint? Because I can.
Screen share. We will share the screen. Stop sharing. Entire screen. Entire screen. Sometimes what happens is they take multiple screens.
And can we then? Ah, it says Google Meet is sharing.
Good.
And it says here that Google Meet is sharing your screen, so they should be able to see it as well.
Yes. Google Meet. Yes.
Yeah.
This is screen now.
Yeah.
फिर सर अगर एडिटेबल भी हो ना सर क्योंकि इनपुट में सर एनेबल एडिटिंग हम लोग शीट का क्योंकि मे भी किसी टाइम में इसलिए यू कैन नॉट शेयर इट नाउ इट इज okay why is this part of
Probably have some people slowly dropping back in as well. From one of the questions, I realized that I haven't defined what a fluid is, talking about microfluidics. A fluid could be either a liquid or a gas, and the liquid can be in any solvent. So it could be an aqueous solution, it could be just water, it could be methanol, it could be ethyl acetate. Anything that flows can be used. Do microfluidics on them. So Fair Andreas. about rectangular channel. To call it microfluidics, one of those dimensions needs to be smaller than a millimeter. We've got the height of a channel, which typically goes in. We've got the cross-sectional area of the channel, which is the width by the height. And then we've got a volume of the channel we can then multiply with the length. What is one of the things that will be coming back in some calculations of a dimensional variable called the Reynolds number is the characteristic length. And the characteristic length is calculated by multiplying the surface area by 4 and divide that by the perimeter. So you look at the ratio of the surface area, the width times the height, and the perimeter, how long it actually takes to walk around it. And that's a way to kind of compare apples and apples if you're talking about triangular with rounded corners, circular channels, square channels, rectangular channels. If you want to kind of put them all together in the same box, you can use that equation to calculate the characteristic length, and that will be important if you start non-dimensionalizing your channels for comparison reasons. Just while getting something to drink, we were talking about Newtonian, non-Newtonian fluids, and we've recently done some comparisons of flows in 200 and 400 micron channels. And to actually be able to compare them, we've normalized them all on Reynolds number that we'll go through in a little bit. So it is sometimes, if you want to compare different fluidic systems, it is very useful to be able to understand under which conditions they fluidically behave the same. And the Reynolds number is something that the engineers use to look at the fluidic behavior and the ratio of inertial and viscous forces, which determine how well things mix and how flows flow. That's probably as far as I can talk without having a great picture. Let's see. So that's the first one again. So we've finished that one. So 1, 2. So I've numbered them all.
I don't know why it shows.
Do we need to just shout? That's scaling laws.
Every time we come back to that one. What is slide's name?
1, 2 scaling laws. So all the ones starting with a 1 are for today. 1, 1 was the first one. 1, 2 is the second one. So 1, 2 scaling laws is what we're doing now. It looks like it's still presenting the previous one. What about we close all the 1, 1s?
Yes.
And then only open the 1, 2s?
सारी स्लाइड्स बार-बार हो जाती हैं.
Just restart PowerPoint?
Yes. Let me change the computer. Oh, ये setting करने का नहीं time लगेगा. उधर
Bridge का
Okay, it's open down.
Yeah, let's see if we can actually from here open 1, 2 as well. Happy to share this one. Site already reached. So then we've got our downloaded version here. That's your decision. The problem is that the PowerPoint license is not.
Enable editing.
Enable editing. How do we now get Google to look at this one again? So, is it this one?
Yes. Sharing audio.
Okay. But it's now not giving the little message that Google is sharing.
I think that is going on. Already sharing.
Thank you. See if I can get my ability to get to the next slide back. Yeah. One of the things that scales really rapidly with size is the time it takes to diffuse from the left to the right. You all may have heard about the diffusion constant, which is the time it takes for a molecule to diffuse around a certain constant. So the distance that a molecule diffuses is the square root of 2 times the diffusion constant, which is different for different sized molecules, and the time. And if we talk about microfluidics, we're talking about hair-like structures, 100 or 50 micron. If we look at an antibody, and I'm not sure if you can actually, most of you can see that. So an antibody, the diffusion constant of an antibody is about 40 square millimeter per second. If we're talking about a small molecule, like acetate, I took here for an example, that goes a lot faster, a lot further in small time. So that goes about 1400 square micron per second. So small molecules are really, really buzzing around, go a lot further than the very big proteins that are really, really sluggish. If you go particles, it goes even slower. So small molecules are fine. You drop them somewhere and they'll just swim across. If you go to proteins, DNA, large molecules, diffusion really becomes a relatively slow process. If we measure time, use a very simple equation, we can calculate that, for a period of 5 seconds, an antibody can move about 20 micron. The small acetate molecule that is a lot more flexible and agile can move by 120 micron, which kind of technically means that in a microfluidic system, if we manipulate that time a little bit, we technically can separate acetate from the sluggish, slow antibody, because they move at very, very different rates. Something at a large scale you wouldn't have considered. We'll be talking about how we do that in a little bit more detail later. But you see that the time scales or the distances, if we keep the time scale constant, the distance that they move by diffusion actually is very, very different between a protein and a small molecule. So it does matter if we all of a sudden play at this micrometer scale, because things that we didn't think were possible at a macro scale all of a sudden become significant. So to cross a channel to get to a detector over 100 micron, for an antibody, it needs to be in the system for 125 seconds. That's more than 2 minutes. Whereas for a small molecule, if that's only present in the system for 3.6 seconds, it's already across. So the small molecule is a whole lot faster crossing an intersection, crossing a channel that's 100 micron than an antibody. We'll be talking about that when that becomes important a little bit later, but it becomes important when we understand a little bit about the different levels of flow. And in our everyday life, flow is turbulent. Life is turbulent, flow is turbulent. So if we look at here a little bit of smoke, if you look at what's happening behind the wings of an aeroplane, if you look at water coming out of a garden hose, if you're looking, you all love your milk in the tea. If you put milk in your tea, that's a beautiful convective mixing process. It mesmerizes me every time that you can just see all the whirling around and swirling. Fluid dynamics is very pretty to watch. In microfluidic country, however, we don't have all those swirly whirlies. Life is linear. Sounds a bit boring, but you can do cool things, and you can get the swirly whirly back as eddies. So life is all good. There's still pretty pictures, but the life where the physics that we're used to, you put milk in your tea, and it goes everywhere in all kind of roundabout ways. And in microfluidic systems, it doesn't work that way, and that's because we're working in the laminar flow regime. Laminar means that, like the what would you call it in English? I don't know the Dutch word. The things that we hear in the window decoration, they're all nice vertical lines. And that's the way laminar flow works as well. It's all very organized, very sorted. And engineers have come up with a really nice way of comparing things based on dimensional parameters. The one for laminar flow, or the one that describes what kind of flow regime you're in, is called the Reynolds number. And I know that I'll be saying it at least once a day in the coming weeks, so I thought that I should just introduce you to what it is. The Reynolds number, if it's larger than 2000, we're in our comfortable twirly-whirly world where we put milk in the tea. If it's under 2000, we're in the microfluidic domain, and that means we're not in our twirly-whirly world. Microfluidic systems quite typically have a Reynolds number anywhere between 0.10 and 10, maybe 15. I think I've worked at 20, but small Reynolds number. Most engineers that have never heard about a microfluidic system get kind of giggly. Oh, that's a very small Reynolds number, because they're used to 2000, 5000. Things get different if you work in a laminar flow regime. And one of the easy ways, and that's why I put a little honey drizzle here, life is actually pretty much, in a microfluidic channel, life is like living in a honey jar. I can substantiate that. So the Reynolds number, it's a number, which means that you can calculate it. So this is the formula to calculate the Reynolds number. And the Reynolds number is dimensionless because it divides two forces by one another. You've got the ratio of the inertial forces over the viscous forces. And you can calculate that based on the density, the velocity, the characteristic length. There it comes back. So that was the surface area, 4 times the surface area divided by the perimeter, and the dynamic viscosity. So we've got the density and the viscosity of the fluid. They're properties of your fluid. The velocity is probably what you do with it, because you're the person doing the microfluidic experiment. And your length scale is the contribution that comes from your microchannel. If we compare different systems, if we have a tub of water here, the density is about gram per cubic centimeter. Viscosity is about 9 times 10 to the minus 4 Pascal seconds. So if we've got a 10 by 10 centimeter tub, just a yogurt container or something, stirring at a velocity of about 10 centimeters seconds, which is quite normal stirring rate. Our Reynolds number is 11,000, big number. Engineers love it. If, however, we put that water, same density, same viscosity, same bottle. If we put it in a 100 by 100 micron channel, which is also a few silica capillary, and we're still moving at 10 centimeters a second, then all of a sudden, our Reynolds number is 11. In the tub, our Reynolds number was 11,000, which is way bigger than 2000. Truly whirly world. If our Reynolds number is only 11, that's a lot smaller than 2000, which they put as a line for laminar flow, which means that we don't no longer have our twirly whirlies. I just said I put the honey in there. Yeah, I like honey. We've got some honeybees that recently took residence in one of the trees on our property. Honey is a bit more viscous and dense than water. And if we buy a honey jar, which if you buy a big jar, we've also got about 10 by 10 centimeter, then our Reynolds number is 1, which is also a lot smaller than 2000 and not too dissimilar from water into our microchannel. So if you struggle to visualize or put your mind to what's actually going on in those microfluidic systems, buy a jar of honey, not very expensive stuff, sugar syrup does as well, and just some food dye, and try mixing it through. Just try putting a drop of the blue dye in, taking a spoon and stirring it around, and you can see laminar flow without having to do any risk assessments, just on your own bench, and it's mesmerizing. It just doesn't do the swirly whirlies, it refuses. And that's how life looks at small Reynolds number flow, and I really like that honey analogy to understand how fluids do what they do. And we'll be looking at a lot of movies didn't work. We'll look at a lot of pictures, and I'll try to get some movies to work as well on what fluids do if we're sitting in a honey jar by putting water in a 100 by 100 micron channel. So that's our friend, the Reynolds number. I just talked already about how you can use hydrodynamic resistance for control by using the electronic circuit analogy. And this is one of my PhD students a long time ago now. When was Adam around? I think this must be 2012, 2013-ish, I suspect. So we had a microfluidic device where we wanted to do cation and anion analysis at the same time, which meant that we had to inject into different channels from the same sample. And we needed to do some calculations on the flow resistance, on how we could actually direct the flows where we wanted them to go. And Adam had a background in electrical engineering, so he made a very nice diagram to there. And we realized that if we just had a very simple microfluidic channel where we didn't play too much with length or doing our calculations, but we added to the outlets of these microchannels, we added big flow resistors, which were just a very long, narrow bore bits of tubing. So we got some 25 and 50 micron bits of tubing that we could buy in 10, 20, 30, 50 centimeter length and a meter long. And we did the sums, which one got closest to what we needed. And we could play with the fluidics happening in our central channel by just attaching different bits of tubing to the outside of our channel, because the flow resistance of a channel, when everything is in series, it's the sum. So you don't actually need to change your microchannel you're doing your separation in if you change the flow resistance in series with that. So that was a nice bit of work. And what we managed to do here was having a sample being introduced in the chip that was pretty much going straight through from the top. So sample came in with some buffer to prevent any leakage, went straight into the waste when this valve was open. And our swirly, should keep on saying swirly willies. Our flow resistors here at either end didn't really do anything more other than preventing any flow going to the outside. We've had a big channel here in the middle, very low flow resistance outlet, high flow resistor here, high flow resistor there. Nothing in that flow wanted even to venture down those microchannels to the sides because the flow resistance was more than 1,000 times higher. No way fluid wants to go there because fluid is lazy. Fluid wants to go the easiest way possible. So fluid went straight in a straight line. Then we wanted to inject some sample. So we had a sample flowing along here. Well, we closed the valve. So all of a sudden, we made it really hard to the fluid because it had the easy way out. We closed the valve, we blocked it, which means that the fluid had to be pushed to the sides, which meant that we created pressure here. The sample could get injected to the left and right. In this instance, we wanted to have the injection the same size, going to either direction. So we had R1 and R2 at the same magnitude. If we would have liked to do unequitable injections, we could have increased the flow resistor here to have a smaller amount of sample plug injected to that side than to that one. And that provides, I still believe, a very nice way of playing around with the microfluidics, of having the planar structure where you need a whole range of intersections, but use the cheap upchurch capillaries that you can buy to play around with your flow resistors to get the exact experimental conditions optimized before you invest a fortune into getting a customized design made up or getting 7 customized designs up where 6 out of the 7 you play with for 2 hours, you say, nah, not quite what I wanted. So after we had a small amount of sample injected, we wanted to play in the interface. So the valve here opened again. We could wash it out. We had a small amount of sample in both of the sides. And then with that one still open, we put the potential difference out and we could do capillary electrophoresis in both of these channels at the same time. So we could do simultaneous cation and anion analysis from the same sample that was hydrodynamically injected, playing around with the flow resistors and a valve. So that's where fluid control gives you new options. Those of you that have been looking really carefully, and I'm sorry that the screen isn't as big as I thought it was going to be, you can see that here there's not just sample coming in, but we've got 2 blue lines as well that say buffer. And what we did there was actually use the laminar flow that we'll be talking about a little bit later, the fact that we didn't have swirly whirlies. Because what an analytical chemist wants to do is have a discrete injection. They want a sample plug that's got a front and an end that are really well defined, and there's no blurry boundaries. So what we did is when we had sample flowing in there, we had sample flowing through the middle of the channel, but not on the sides. On the sides, we had a little curtain, we called it, of background electrolyte, which meant that we had the time that our analytes took to diffuse through the width of the curtain was longer than the time it took from them to get past that intersection. So none of our analytes could actually find its way to the separation channel while we were loading the sample. Here you can see that the 2 blue lines are not on. So we temporarily lifted our shielding curtain, allowed our sample plug to all of a sudden take the whole way, push it into the channels, and then quickly close the curtain again with background electrolyte. And that allowed us to inject a really nice clean sample plug. Hydrodynamic, so it still had a parabolic profile at the front, but a very well-defined sample plug. So that's the laminar flow trick that we played in this bit of work. And here you can see with different food dyes what we did. So the background electrolyte here, so it was a 300 micron channel. The background electrolyte here is visualized with the yellow and the blue food dye. Our analyte was sitting in the middle. It had been temporarily lifted so that the whole channel, for a very short period, the whole channel was red. We then closed the valve, and I doubt you can see it from your position. But there's actually little injected zones of red dye you can see on this microscope image when we just close the curtains again to prevent any more of our sample leaking. This image in here, we'll go through a couple of them. This is how it will look like when you start tonight at home mixing your food dye in your honey jar. Or this looks what water does in a 300 micron channel. Just like the things that are hanging at the window. Straight lines, no weird things, no swirly whirlies, beautiful straight lines, even at the corners. And that's the way that laminar flow looks like. That's the way that flow systems look like if your Reynolds number are around 1 or 10. It's probably more 10 here in this system. So that's the way that we can play, and that's where these Reynolds numbers, as well as the flow resistors, as an analytical chemist, you need to be able to kind of play with them. Laminar flow is used in a very interesting concept called the H filter. Not to get onto the engineers here at the moment, but engineers tend to be kind of very direct and straight. The H filter is called an H filter because it looks like an H. 2 legs, 1 cross intersection. That's why it's called an H filter. It looks like an H. But it's a really smart way. If you remember the first slide, we talked about the diffusion times, and I told you that antibodies were really slow, small molecules were not. This H filter is made to extract the fast-moving stuff without getting interference from the slow-moving stuff. Because if you inject slow-moving stuff or a mixture of slow and fast-moving stuff here in the purple line, and you've got your acceptor with your buffer going on the other end, the fast-moving acetate will be able to move across, and you get almost equal concentration on both sides, depending on how long your H filter is. If your residence time in your H filter is short enough that your antibodies actually don't make it across that line, and for the 2 that do, you make the flow rate here a little bit higher, or the resistance there a little bit higher, so that a little bit of your buffer flow gets skimmed off into your waste. Then you get none of your antibody coming in there, but half your acetate will end up in your acceptor flow. And that's the way that the H filter works, and it's a really nice structure where you can use laminar flow to do extraction or dialysis like sample preparation steps without even needing a membrane. So one of the nice things of an H filter is that it's called a filter, but you don't need a membrane or anything in the middle. The only thing it relies on is laminar flow and the difference in diffusion constant between particles and small molecules and or proteins and small molecules. So very nice concept. And there's the laminar flow. I think we'll come past the other example, but I'll just already put in your mind. One of the really nice commercialized examples of the H filter has been a sperm sorter, because like diffusion constant, there is a difference in, so sperm, it's the good swimmers, the mobile ones have high mobility, high fertility rates. The slow sperm are the not so good swimming ones, are the low fertility rates. In fertility clinics, they want to get the good swimmers out. If you put them in a microfluidic system in an H filter, the good swimmers will swim to the acceptor stage, whereas the poor swimmers won't be able to do that. So if you get a sperm sample through an H filter, you can collect the good swimmers at the other end, whereas all the poor buggers, the poor swimmers that you don't want to do your IVF with, they go to the waste. This was one of the first commercial products. I think it was 2004 it got commercialized. And I remember seeing a photo probably now about 7 or 8 years ago with the first generation of microfluidic babies. So they actually applied this to human samples and did IVF with microfluidically sorted sperm. And yeah, the kids, they were then almost 10, so they must be now in the mid-teens. So and this is being routinely used as a sample preparation approach now before IVF, using an H filter to separate the good swimmers from the bad swimmers. Laminar flow is pretty, and there's the Forge lab, and if you want to have either get a little bit of an idea of what microfluidics can do, but also look at some pretty science pictures. The Forge lab in the US has put a Google Photos page together where they purposely made microfluidic designs and did microfluidic experiments to be pretty. And there's a lot of nice pictures in there. And here you can see a system where there's a couple of valves involved, and you can see the laminar flow, and you can see how beautifully, if you've got your microfluidic system balanced. That's why I talked about the balancing and the siphoning, because it's not always easy to get your flow lines to sit where you want to have them. But here you can see the different flow lines. You can see that this one splits nicely in the middle. It splits again, and then it goes in there. And you can see that the flow lines stay beautifully separated, and there's only diffusion going in, which is why I like this part as well, because you can finally see here, you can see the lines blurring up a little bit, and that's where you get the small molecule diffusion, and the lines get wider and wider. But it is, yeah, it's mesmerizing to look at. There's a lot of things you can do with microfluidics and laminar flow. I like this one as well. We already talked about the interfacing. It's not easy to get the fluidics all controlled as well as you can. And this microfluidic system here is a combination of a whole range of different fluidic systems. Are we happy with Nitesh Kumar to come to our meeting? So here we've got a microfluidic infrastructure where you can see the different fluidic connectors. You can see that they're just normal silicon tube, the flexible tube you can get anywhere. These are little non-sharp needles, so they're stainless steel tubes. It's a silicon rubber chip where you can just push those metal tubes in. They stay in place, no super glue required, which is really nice about PDMS devices. And you can see them all having their little fluidic inlets and their microchannels. And then there's a whole range in here. They don't control fluids, but they don't control the liquids, they control the gas. And there's some pneumatic valves in there that allow for even finer control. But you can see here that creating the microfluidic infrastructure is like a printed circuit board. It's not that hard. You need to think about all the architecture that you need out there to interface with your outside fluids, because one of the big challenges in microfluidics remains how am I going to get my fluid where I want to have it in my chip when I want to have it there. And so this is a nice other picture showing some of the infrastructure. And by accepting someone into our presentation, I think I know now, yeah. We just talked about that here, about how we can calculate with the flow resistance. And I hope by having shown you some of the more complex devices, it actually starts making sense that at a certain point you need to start being able to calculate where your flow resistors are if you want to play with them. So there is a slight difference in the hydrodynamic resistance for cylindrical channels and rectangular channels. So if you work with them, get the right formula out, look it up somewhere. So we will do an assessment by the end of this course. If you'd need any kind of equations, I'll give them with the exam. I don't think there's any need for any of you to start memorizing how to calculate a Reynolds number. So I may get you to calculate one because there's an example in there. If I do ask you to do that, then the formula will be given. So don't spend tonight memorizing the Reynolds number and wondering what the units of the viscosity were. Your units will, I don't think anyone in this room will be a better person if they know the equation for the Reynolds number. So don't bother memorizing it. Be able to work with it, that's important. If you look it up, you should be able to do something with it. So if we look at microfluidic scale, hydrodynamic resistance are different. The flow itself is different. We have laminar flow. The other thing that's different is that the surface effects become more pronounced. And again, I like my real life examples. If we look at the animal kingdom, we've got people with a high, or animals, creatures with a high surface to volume ratio and with a low surface to volume ratio. Low surface to volume ratio is our elephant. Big animal, not a lot of skin. If we look about a mouse, we actually have got a very large, and a small volume surface to volume ratio. So for animals, it actually makes a huge difference in how much food you need to stay alive. And a mouse needs to have a much higher energy intake because it's not very efficient. A mouse has got so much skin and all that skin is always leaking warmth. Happily, we've got a lot of heaters, but we still got a lot of surface area in this room, so a lot of our heat dissipates out. A mouse is continuously busy staying warm. Whereas for an elephant, it's not that much of a concern because it's got so much critical mass in its body that a little bit of skin that sits around doesn't dissipate that much of its heat. So if we've got a large surface area in a small volume, we dissipate our heat very differently. We dissipate our heat much more efficiently. The fact that it's efficient is not always good because that means that that little mouse is always eating, including from my pantry, because it's always hungry. But it means that in microfluidic system, our heat control actually can be really efficient because we've got a lot of surface, little volume, which means our temperature control is a lot better. So, and that also means that we can be a lot more accurate. So if we want to heat a microfluidic system, it's a much easier to ensure that we've got homogeneous heat distribution in our picoliter of liquid than it is when we have a large kettle of, or we're boiling tea or soup. So having a different surface to volume ratio has got important consequences for our heat dissipation. As a chemist, it also has some consequences for the importance of the surface of what we're doing. If you're an organic chemist working with a round bottom flask, your surface to volume ratio isn't that big, so the glass doesn't play such a significant role. If you're miniaturizing down, the relative importance of your glass surface actually becomes larger and larger and larger, up to the point that you can start using your surface of your microchannel, an absorbent stationary phase for immobilizing molecules, because there's so much surface relative to the volume. We've moved on here. So if we look at a centimeter scale, so we again have got our kind of yogurt container, 10 by 10 by 10 centimeter. Our surface to volume ratio is about 60 to the beta minus 1. which becomes 600,000 when we go to a 10 by 10 by 10 micron cube. So we get a lot more surface for our volume. And that's heat dissipation as well as surface effects, which would be great if you want to immobilize something, which becomes a pain if you're afraid of fouling of proteins, because you've got a lot of surface that your protein can foul in the microfluidic channel. So a lot of good things, some of the things you need to be aware of as well, because problems can get a lot bigger. The next thing I want to talk about, and will be getting quite complex, is understanding capillarity. And that is the way that we've got a much more important surface, which means that our surface starts playing a role as well in how our system's wet. And we can even start playing with that as a driver of fluid. We've all probably put a straw into a liquid and seen that the liquid rises if we've got a hydrophilic straw and we put it in water or soft drink, we can see that the liquid rises. And it rises higher if the tube is smaller. So we have a more force to overcome gravity if we have a smaller diameter system than when we have a larger diameter system. Which is where the capillary number becomes an important characteristic, which is the ratio of the interfacial forces, the walls pulling, and the viscous forces, how hard is it to drag the liquid up into the channel, or if it's horizontally. We don't need to fight gravity in the process. So we've got the dynamic viscosity, the velocity of the system that it's working, and a sigma, which is the interfacial tension, which is a way to measure the energy that sits here between the surface and the droplets of liquid. Droplets, we won't be talking a lot about droplets, but that's one of the things that talks about immiscible fluids and the surface tension as well, which is important to know. One of the areas of microfluidics is working not in continuous flow system, but in discontinuous systems. And here we've got an example where we've got a channel where we've got an oil and water, and based on the surface tension differences, our water actually wants to be together, because we've got liquids that like each other and we've got liquids that don't like each other at all. If you've got them in a large system, they'll form two different layers, and the heaviest one sits on the bottom, the lightest one sits on top. If you put them like this, you pump them together in a microfluidic system, they form little droplets sitting in a train behind one another. So we've got a dispensed liquid that sits in the other liquid. So the droplets that are formed, they are function of the surface tension, and the surface tension itself, it can drive the fluid motion well, because it applies a force. So the capillary forces themselves, they can draw liquid channels when the solid liquid interfacial energy is lower than the solid gas interfacial energy. So if there's an energetic preference of the liquid surface to be wet rather than to be dry, it will be filling itself. And then that's beautiful, because if you want to fill your microchannel, it wants to be filled because the solid liquid interfacial energy is lower than solid gas interfacial energy, which means that you only need to put a little droplet in your reservoir. And your channel, if you've got a certain, it very much be filled away by the end, because the walls pull the liquid through the channel, which makes life really easy. So a couple of the examples of the droplets that I put them together, of the droplets and the interfacial energy, there were no surface tension. And for those of you that don't have the chemistry background, you can a way that you might have seen it in real life is that there's wetting surfaces and non-wetting surfaces. If you've got a raincoat, it will be hydrophobic, so a droplet will form. So on a raincoat, it wants to repel water, so droplets of water will be beating up. Whereas if a tea towel, you don't want your droplet to be beating up, you want it to suck up water, so it will be hydrophilic. So there's different ways that people have looked at it, how droplets form at the surface. And what's important in calculating the surface energy is the contact angle, which is the angle that the droplet here makes with the surface. And you can see here that there's, when we've got low surface tension substrate, we can see that the droplet is all the way beaded up. So we've got a very large angle. And when we've got a wetting surface, we can see that the droplet's all flat out, and we've got a very small angle. And that's the function of how compatible the liquid and the surface are together. This one will draw your liquid into your tube. This one won't. To put some numbers behind them, merely for the calculations that will be on the following slides. There's some examples here of the difference in surface energies for different liquids here, and between, so water on a few silica interfaces and a couple of different contact angles. Again, if I want you to do any calculations or think about them or predict what's going on, all the numbers and the variables and equations will be given. It's about being able to repeat them with the equations given, because I don't think anyone benefits from memorizing a lot of equations. So a hydrophilic surface is defined as a surface that...
Then after lunch also it has to start and continue.
So we can take a break now?
Yes.
Okay.
I think.
We started with late. Let's see how many...
You can always continue. You can always... Leftover part you can always... Leftover part we can always share after in the second second part. No problem.
Okay, because I don't...
So 1 2 is the lunchtime.
Yeah.
For you also.
And we started a bit later, so I didn't.
Frustrated like this.
So let's quickly see. Yes. So that's the... I'll talk you through the basics. I'll share the slide materials with you anyway, and then we don't talk through the equations, and we can just wrap this session up in 5 minutes. So we can calculate how long a water plug would be. One of the nice things about the wetting is that we can actually have droplets moving uphill. There's an area that's called digital microfluidics, where you can use an electrode to change the wetting. We've talked about that one. How high is not really important at the moment. How fast is not important. This is the only one I want to have you guys having in mind, because we have looked at the straws, how they wet. Porous materials wet as well. You know, paper towel, paper wets water. And the way that does that is that through the Lucas-Boschborn equation, which is also related with that contact angle between the liquid and the solid. So if you've got paper which is hydrophilic, it will take up water, which will be important when we start talking about paper microfluidic devices. And it will do that at up to the height that corresponding to the contact angle, the surface energy and the viscosity of the liquid. So this is the part where we'll be getting back into if we go into the paper microfluidics lecture. Other than that, all the maths will be you'll get all the lecture notes. It is just following the equations. All the parameters are defined in there. So I'm quite happy to break up for lunch if you promise me that you remember that you know that low Reynolds number flow means that we don't have swirly whirlies. We have laminar flow, so our channels, the flow looks like our window dressing here. Mixing becomes a challenge, and that's why after lunch we'll talk about why sometimes it's nice mixing as a challenge. So we'll revisit that H filter a little bit. And we'll also talk about different ways that we can realize mixing on the microfluidic scale. Surface to volume changes. which means that we got much more efficient heat dissipation. We get also better control in heating, so we can, if we do thermocycling for DNA amplification on a microfluidic device, we can actually do that a lot faster than in an Eppendorf tube because our surface to volume ratio is so much better. Surface effects are really important. Wetting with that is really important. Capillaries can draw liquid in. Hydrophobic patches can be used therefore as a valve because they stop that whole reaction of drawing in, which will be very important if we start talking about paper microfluidics. I think it's early next week. Enjoy lunch. He just saved you from the most horrendous bits of physics. Yeah, give him a coffee. Or tea, or whatever you need to bribe him. Or maybe you already did that. Thank you. What time will we be back?
1 hour.
1 hour? Hey, worst bit done. And he saved you from all of it.
So we can have 1 hour break for lunch. We'll assemble it back. ਗੇਟ ਤੇ ਕਿਹਨਾਂ ਦਾ ਨਾਮ ਘੁੰਮਣ ਵਾਸਤੇ ਬਸ ਬਣ ਗਿਆ ਉਹਨਾਂ ਨੇ ਕਿਹਾ ਮੈਂ ਉਹਨਾਂ ਨੂੰ ਜਾ ਕੇ ਗੇਟ ਤੇ ਐਂਟਰੀ ਕਰਕੇ तो राइट हैंड साइड पे एक पास वाला पास सेल है उन्होंने कहना केमिस्ट्री डिपार्टमेंट से मेल आई होगी तो डॉक्टर जितेंद्र सिंह वाला को अगर नहीं बनाई होगी तो रिक्वेस्ट कर देंगे दोबारा ਤੁਸੀਂ ਭੇਜ ਦੀ ਇੱਕ ਵਾਰ ਮੈਂ ਕੱਲ ਭੇਜਦਾ ਸੀ
I joke that they capillary forces will die. That's all. That's what it was.
So how is the time to go to yes sir yes Melissa you can walk right just to see ਗੁਰਦੀਪ ਬੜਾ ਇੱਥੇ ਰਹੇਗਾ ਸਾਰਾ ਇਹਨਾਂ ਦੇ ਇਹ ਧਿਆਨ ਰੱਖਣਾ ਇੱਕ ਜਣੇ ਦੀ ਗੱਲ ਆਪਸ ਵਿੱਚ ਕੋਈ ਵੀ ਡਾਲੋ ਲੇਕਿਨ ਇਹ ਨਾ ਹੋਵੇ ਕਿ ਸਾਰੇ 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 ਇੱਕ ਦੋ ਜਣੇ ਜੋ ਹੈ
ਲੈਕਚਰ ਦੋਨੋਂ ਤੁਹਾਨੂੰ ਕਹਿੰਦੇ ਨੇ ਕੈਸ਼ ਤੋਂ
ਹਾਂ ਔਰ ਸਟੇਜ ਦਾ ਵੀ ਇਹਨਾਂ ਦਾ ਦੇਖਣਾ
ਇਹਨੂੰ ਨਾ ਥੋੜਾ ਗੁਰਦੀਪ ਇਹਨੂੰ ਸੈੱਟ ਕਰ ਲੈ ਯਾਰ ਉਹ ਸੇਵਿੰਗ ਕਰਾ ਤੇ ਵੀ ਫਾਰਮ ਨੂੰ ਉਹ ਫਾਰਮ ਨਾ ਬਸ थोड़ा जा माइक के साथ
नहीं एक कैमरा ये सिर्फ कैमरे की रिकॉर्डिंग नहीं करनी है हम ऑडियो लगा रही है तो ये स्पीकर नहीं ना साਡਾ चलो करनी है
ਉਹ ਫਿਰ ਤੇ ਨਾਲ ਹੀ ਲੱਗਣੇ ਕੈਮਰੇ ਦੇ ਨਾਲ
ਇਹ ਸਿੱਧਾ ਕੈਮਰੇ 'ਚ ਜਾ ਰਹੀ ਹੈ
ਨਹੀਂ ਇਹਦੇ ਨਾਲ ਲੱਗ ਗਿਆ ਸਪੀਕਰ
ਨਹੀਂ ਉਹ ਤੋਂ ਫਿਰ ਐਕਸਟਰਾ ਹੈ ਇਸ ਸਪੀਕਰ ਨਾਲੇ ਸਾਊਂਡ ਸਿਸਟਮ ਦੇਣਾ ਹੈ ਕੋਈ साउंड देखते नहीं तो लोकल है क्यों कैमरा अंदर नहीं करना ये लॉक नहीं करते बट और क्या है
काफी बार कर रहा है
using the how do you like to yourself often? Okay, I used to be on the
हो गया हाँ जी सर ठीक सर उन्होंने वास्ते ना ऑफिशियल लेटर फिर वहाँ हाँ वो कहते कि ऑफिशियल लेटर है नहीं बोल सकते मैं ਉੱਥੇ ਐਂਟਰੀ ਦਾ ਕਰਕੇ ਆਇਆ ਉਹ ਕਹਿੰਦੇ ਕਿ ਫਿਰ ਉਹ ਚਾਰजेस ਦਾ ਫਰਕ ਹੈ ਨਾ 250 ਪੈਂਡ ਦੀ ਅਦਰਵਾਈਜ਼ 600 ਪੈਂਡ
हाँ जी जी मेरी आज या कल अच्छा एक बार
We got friends. Just sit down. I'm not used to people standing up when I enter a room. It's working.
हाँ बलजिंदर जी ये जगह आई ना मैं यहाँ पे लिख के दे दूँगा कोई और नहीं सर मैं लिख के दे दूँगा नहीं ना तो बैठ सकते हो बस ठीक है मैं लिख के दे नहीं नहीं मैं आपको देख रहा हूँ
ठीक है नहीं नहीं ठीक है
अपनी फाइल में लिखा है
What time are we starting again?
They're going to lunch actually, and if they're coming back, they'll take the time. You think loss are better? Right?
Just let me know.
You can start. They will keep
Meeting up.
He has his group meeting. What time are we?
Proceed to phone for them.
Pressing the button.
Or I know
Also to 9 on a
शुरू करा दें.
To start? Okay. So I hope you all had a great lunch. I certainly did. Lovely food out here. So we have 2 more lectures going. I think it is. Just put something in the chat today. So I don't know if they can see the slides that you're.
That's good.
Yeah. And they want to see that one. Not sure why it's extended, but it seemed to be working the previous session. Yeah. Okay, I've got control. Yes. So we've done some of the fundamentals on what's different in microfluidics than in the normal everyday systems. One of the things that I said was hard was mixing. So we'll have one session now on how do you actually mix under laminar flow conditions. And then I've got a presentation put together with a couple of different examples of what microfluidic systems have been used to get you a little bit of a bird's eye view where all that fundamental physics is used to. And 4 lectures on the day is a lot, so it's also a little bit of a sit back, relax, and see what all is coming across you, because I've taken a couple of different examples across different fields to make you aware of what's going on, and then we'll do some analytical chemistry tomorrow. So we'll be starting off with some way of mixing things when we're in microfluidic systems. Because as we know, the volumes, if we go microfluidics, are becoming really small. And with those small dimensions means that diffusion times start to matter. For example, we looked at the H filter, where we are able to isolate or extract small molecules from large molecules because of their differences in diffusion constant and therefore the time it takes to travel across a certain distance. And we had an antibody displaces 20 micron, a small molecule 120. So if you are assured over a 5-second period, that may be the residence time of your mixture in an H filter. If that 5 seconds, if you make sure that 20 micron wide of your flow in your H filter goes to waste, you can be reassured that none of your antibody will make it into your collected stream. But at the same time, you can get at least half of your, or about half of your small molecules out, because eventually you'll get at an even distribution with an H filter. That's one of the things to keep in mind. It's not the preferred phase, so the best you can get is equal concentrations all around your channel. It's not that your small molecule can be extracted with 100% yield to the other side. The best yield you can get with an H filter is 50%, because nothing else but equalizing concentration, the concentration gradient is driving the difference. So as soon as you've lost your concentration gradient, you've just lost driving force and you're not getting any higher concentration in your acceptor phase. If you'd like to get to higher yields, you may want to use immiscible fluids and do liquid-liquid extraction in the same geometry. That's the point where you could get to higher efficiencies. But then the yield of an H filter is limited to 50%. And quite typically for small inorganic ions where we've used, it's typically sitting around 35, because you need to skim off that little bit to prevent contamination of your acceptor phase with your donor phase. So 35-40% is quite typically where people using the H filter for analytical purposes, where that sits at. The Reynolds number. We were talking about laminar flow, where we don't have the twirling mixing by convection, but our mixing is only based on diffusion, which can be good, can be a challenge for mixing. So what about mixing? And here we've got a T junction, which is pretty much half an H filter. Shouldn't take too long to warm up again. So the thing that we'll be looking at is when we've got two different solutions coming together and flowing next to each other, how actually that diffusion boundary works like and how it looks like. And what we have there is one solution that contains some, I think it's fluorescent dye. One of them contains normally water, and we'll have a look to see how the flow profile develops if our technology wants to cooperate. There's nothing projecting yet. Yeah, there's light coming. Yeah, there we go. So we've got our T intersection where we've got two different flows coming, and here you can see it slowly coming up. One's got a color dye in there, the other one not. We'll be looking at what's happening at the interface. So if we look at that a little bit from the channel in, it's not just fluorescing. So we've got a reaction taking place here that forms a fluorescent project between fluorophore and calcium chloride. So you can see the Y intersection here, where the flow is going, and we'll be looking at how this interface here looks like at different points in time. Some people already asked me the clever question, how does the flow profile actually look like? We've got pressure-driven flow, and therefore we've got the Poiseuille formed plugs, where we indeed get a parabolic flow profile. And an artifact of that you can see drawn here, where you can see the difference behavior at the edges than in the middle. So in this paper that was published in 2000, they looked very closely. They had a nice confocal microscopy system. And this is how the diffusion zone actually looked like. So we've got, I'll do it with my mouse rather than with my hands for the people that are watching along digitally. So here we've got the top view of the device. So we've got the two channels coming together, indicated here by the dashed line. So we've got one channel coming in here with the fluorophore, one channel coming in with the calcium chloride. And you can see here at the intersection, the two reagents, they mix together, yielding a fluorescent product. The further you go down, the more diffusion there is. So we get both the fluorophore diffusing one way, the calcium chloride diffusing the other way. And as a function of that, we can get a wider and wider product. You can also see that it's deviating from the middle a little bit because the calcium diffuses faster than the fluorophore, and therefore we get a little bit of a bias towards the one side of the channel. The images that are under C are not taken from the top, but are taken confocally. So they're projection in the Z direction, where you can see the parabolic flow profile taking place. And you can again see that the boundary, because of diffusion, we get more mixing, we get more reaction product formed across a larger width of the channel, the further we're down, because we're simply spend more time, and more time means a longer diffusion distance. So the question, is mixing driven by convection, by swirly whirlies, or by diffusion, is answered through another dimensional parameter, which is called the Peclet number. And similar to the Reynolds number, this is defined as being the ratio of convection and diffusion, which can be calculated by the velocity, linear flow velocity, the length that you expect this diffusion to take place of, and the diffusion constant. So the length scale of the flow, again, has got something to do with that typical length, and is 4 times the area over the perimeter. For microfluidic setup, rather than calculating everything back to the standard SI numbers in meters, it is the easiest if you just keep everything in micrometers. So you talk micrometer seconds, micrometer square seconds, and it's a dimensional number, but it just makes the calculations a lot easier. So if we've got 10 centimeter a second speed in a 10 by 10 centimeter channel, so a big tube, a small molecule has got a large Peclet number, 7.1 times 10 to the 6th. So that's how convection-driven diffusion works, like 7.1 times 10 to the 6th. If that's the number coming out of your ratio, you can say that your diffusion is absolutely negligible, and convection is the reason of mixing your small molecule in your system. However, if you go 10 micrometers a second in a 10 by 10 micron channel, for the same small molecule with a diffusion constant of 1400 square micron per second, then your Peclet number is only 0.071, which means that we've got a system where we don't have convection, and our mixing is dominated by diffusion. That's where the Peclet number is used for. And microfluidic systems, they're systems that typically have a low Peclet number because our mixing is a diffusion-based process. If we want to then determine the length that we need to require to get a homogeneous mixture of an analyte, for example, we want to measure calcium concentration. So we just had the fluorophore and the calcium chloride to yield the fluorescent products. Imagine we've got an assay where we want to use that to quantify calcium. That means that we want to ensure all our calcium analyte has been mixed to the fluorophore. So it's useful to know what the length is that we need to realize that mixing. We can calculate that as well, because if we know the Peclet number, then it means that we can also calculate the time that it needs to mix, and through the time and the flow rate, we can derive what the length is that we need to mix at this Becklet number to get homogeneous distribution across. So we need 7.1 millimeter length for BSA to diffuse all the way across if we've got a Becklet number of now Becklet number was 70. Yeah. So if I've got a Becklet number of 70 for at 50 micron per second in a 100 by 100 micron channel, we need 7.1 millimeter. So here we've got a similar system, again, 100 by 100 micron channel. We did determine that we our length L mix when we start getting some mixing is 7.1 millimeter. So if this is less than 7.1 millimeter, our BSA doesn't cross that line. Our small molecule already reaches the point where a significant part does cross the middle line at 375 micron. So if we have between 7.1 and 142 seconds, or at 50 microns per second, we can have our H filter, if the length of our H filter is between 0.36 and 7.1 millimeter, that means that we can separate the small molecule and large molecule. Any shorter channel, we don't have anything extracted yet. Any longer channel, our BSA will be moving into if we work at a linear flow velocity of 50 micron per second. Numbers will all change through the equations if we change our flow rate. So this is the picture of the illustration that I already told you, where an H filter-like concept has been used for the separation of sperm based on motility. So we've got the the mouse doesn't show up here. Okay, I'll point at 2 points at the same time then. So here we've got the inlet where we've got the sperm cells, we've got the acceptor phase, and here at the outlet you can see that some of the sperm has migrated into acceptor phase, whereas a lot of it is not very motile and just moving straight along. The graphical illustration is probably easier to see that, where you can see the dead ones that are not good swimmers are just happily going along with the flow, whereas the happy motile ones swim into the acceptor phase and are good for use in IVF. And here you can see the percentage of the motile sperm is significantly enhanced after having passed through a very simple microfluidic device. This is easy to make. It's channels where, well, they've got different depth here, a different width here, but it's really just two channels coming in, having a section, I think it's 1 or 2 centimeters long, where the channels are in parallel. So it's 2 inlets, 2 outlets, 1 joint channel, and you can get significant enhancement in sperm motility by just passing the sample through that interface. So laminar flow is really nice, but mixing is a challenge. And the question then comes up, how can we mix? And there's a whole range of different ways that we can do it. We can do it passively, just using the pressure from the pump, where we can use different ways of injecting fluids. We can make droplets where we can either inject segments of different water-soluble analytes, or we can use 2-phase systems where we've got a water in oil or an oil and water system. We'll show you later, we can use lamination. So instead of having 2 flows sitting next to each other and waiting for that diffusion boundary to get all the way across the width of the channel, we can also chop the flow in a lot of different segments and have blue dye, red dye, blue dye, red dye, blue dye, red dye. That means that we've got much thinner, shorter distances to diffuse across and a lot more surface area for diffusion to take place at, which then also means that we get a faster diffusion because we have the diffusion process happening in parallel. And that's lamination. You can do that in parallel, but you can also do it sequential, having different segments and then having them blend in the direction of the flow. Oh, my mouse can't go there. So we've got you can get the flows to collide together to still get some mixing going. You can increase the diffusion by taking a very narrow channel. Again, you increase the surface area by increasing the surface to volume ratio between your fluid interfaces. Just having a single contact, using the either vertical or horizontal lamination. You can put some disruptors in flow and mix that way. And the other part that we'll be talking about later is active ways for diffusion. In the very simplest way, you can put an impeller or a little stir bar in a microchannel that will mix things up. You can use pressure-driven systems where you either have a pneumatic valve that disturbs the fluid, or you can use a pump that doesn't continuously deliver fluid, but actually intentionally give fluid pulses. And that again enhances your boundaries and increases your mixing. There have been magneto-hydrodynamic systems that I'll show a picture of later. That actually means electrokinetic, using AC fields where you get analytes to migrate from one direction to another. Very nice way of doing mixing. Dielectrophoresis by using asymmetrical electrical fields. Acoustic fields have been used for mixing as well, particularly when it's involving particles, because particles get trapped or get moved in acoustic fields going to the pressure nodes. Changing the acoustic fields can be used to enhance mixing as well, and you get pressure points where you can create little eddies. And thermally, you can locally change viscosity, which can create flow disturbances as well, that allow you to mixing. So there's this is not an inclusive list. There's a whole range of other ways of doing mixing. So there is a big toolbox if you need two different analytes to mix. And it then depends if you want to do active or passive. Do you want to complicate your chip design for having a passive mixing element in there, for example, structuring the bottom of a channel? Or do you want to complicate your setup by having a heater in there to be able to do thermal mixing, or a little speaker thingy to create an acoustic field? So the active pumps always rely on additional instrumentation, which means that your fluidic system stays very simple, but your instrumentation gets more complex. Passive mixing modes are not very demanding on your instrumentation, but you get a little bit more complex design, and that may have some implications. For example, if you're working with cells, a lot of these passive mixers create local pressure nodes. If you're working with very sensitive cells, they may accidentally lyse whenever you use the passive mixing. So you may then decide to go for an acoustic mixing, which is a lot gentler on cells. So there's horses for courses. You can have a Ferrari, you can have a Toyota. Both of them are cars. If you want to get really, really fast somewhere, the Ferrari may be the better option. If it's just there to get from A to B, or you don't have a huge amount of money, then the Toyota may do the job. Or just even a bicycle may do. So the first question is, when we just look at diffusion, how much do we actually just want to simply increase the length? And I put a picture in here of a serpentine channel, which is a very efficient way to get a long channel in a small footprint. So you can see the channels snaking away. That means that you can actually get a long channel into a small chip, which is particularly important if you're working with a relatively expensive substrate. Like glass chips are relatively expensive to make. You get depending on the clean room that you work in, you get 3 or 4 inch glass wafers. You need to fit your whole structure in there. 10 centimeter, if that's your whole device. You can't put a 15 centimeter channel on there, even if you want to. But if you put some curves in, it's actually not that hard to achieve a 15 centimeter channel. So serpentines are good there. If we've got a total flow rate of 0.1 microliters a minute in 100 microchannel, our minimum length that we need to get some mixing can be derived from Peclet number. And if we do that with acetate, which was our small molecule with our 1400 diffusion constant, we can actually see that our minimum length to get any mixing at all is 2.4 millimeters, which means that the time under these conditions is 7.1 seconds. If we look at BSA, which is a lot slower to diffuse, again, we can calculate the length, and that will be 47 millimeters. That becomes a really long channel to put somewhere. If we assume for a serpentine channel that half of our channel is half of our surface area is taken by the channel, the other half by glass, we can say that we can still fit it into a microchip if we have our channel making 7.5 turns. So 2.4 millimeter on a chip layout is still easy to do. So if we want to mix acetate all the way through or another small molecule, then we can probably just get away with doing it in a straight channel. If we want to work with a larger molecule like BSA, that's got a much slower diffusion constant, we would need a much longer distance to be able to get any diffusion at all, which then means that we are best off getting a serpentine channel where we've got 8 turns in there, and that means that we get the BSA mixed through a microchannel. The time that it takes there to diffuse is the 140 seconds. So a great solution is, if we want to increase the channel length, is to add the turns. We've done the sum test for the BSA, how much you need, but there is a limit also to the number of turns you want to do. And the other trick that we've got in the toolbox there is to go for parallel lamination. Let's see what I did there with the calculations. So if we want to have a chip that's no longer than a millimeter in length, because of the footprint that we have, but we actually need 47 millimeter channel to mix the BSA, our length that we get is 1/47.5 times smaller. That means that our time that we actually have available for mixing in that channel, if we use the same flow rate, is only 3 seconds. So just with a normal channel doesn't work, but if we go for parallel lamination, so just break the flow up in vertical segments, if we've got n layers, the time that we can get that mixing done with decreases with 1/n. So if we then, our time spent L/n square over the diffusion constant, if we use this equation here, that means that if we want to have a residence time of 3 seconds in this cell, then we can realize that if we do parallel lamination in 6.9 or 7 different channels. So if we have 7 alterations of blue dye, red dye, blue dye, red dye, blue dye, red dye, sitting alongside each other, we can get the same level of mixing in a 1 centimeter channel as we can get in a long serpentine. So final outcome is a mixed solution. One takes a long channel with a lot of serpentines, the other one takes a much shorter channel where you need to have a lot of different inlets to be able to vertically segment the different fluids next to one another. There's people get creative, so there's a whole range of ways that you can actually get this parallel lamination to work effectively. So you can have, in the first stage, there's 2 different flows that come in through the inlets, they get together, then you can split them in half, so split them vertically in half, and then recombine them, so you get 4 in parallel. You can split them and recombine them again, and you get 8 in parallel. So that's another option, rather than having a lot of inlets, is actually increase the number of points where the different liquid flows touch one another to do a split and recombine mixture. And you can see in here that the number of contact points and therefore diffusion speeds increases really rapidly if you split and recombine the flows to get the mixing to become more efficient. Another option is to put obstacles in the microchannel that create little diffusion eddies at the corners. And there's different structures that work really well under different flow rate regimes or different Reynolds numbers. So if we look at high flow rates, high Reynolds numbers, you can create the eddies by having obstacles in the channel. So here we can see that there's little areas where the channel contracts and expands. At those corners, you get circulatory flow that aid your mixing. In a similar way, you can create these circulatory flows by putting some pillars or posts in the microchannel. And lastly, just having some 90-degree turns. The flow wants to go in one direction. It hits that flow, and you create eddies in corners as well by abruptly changing the direction of the flow. If we go to slightly lower flow rates or moderate Reynolds numbers, then we need slightly different geometries. We need to put a little bit more effort in. And as you can see here, we've got here one part of the flow takes the short path, the other one has to take the long path through this curved surface, creating pressure drops in the engine here, which means that we get circulatory flow. Again, same thing happens here, same thing happens there, and we get mixing happening in the channel. Another here is split and recombine, and we get an abrupt change to go up, another abrupt change, a narrow area, another abrupt change coming down. All these corners, all these edges, we get circulatory flow, we get mixing. C and D work very similarly. This one here is a split and recombine one, so you can see the flow being split here, mixing here at the sharp corner, here and there at the sharp corner. And then here, the two different fluids, this one meets that one again, split and recombining them again, increasing the interface area, creating much more efficient mixing. That one does a very similar job. So there's a whole range of geometries that people have come up with, mainly through computational fluid dynamics packages like COMSOL, to get proper mixing over very short distances. And one of the challenges, particularly for analytical chemistry, if you want to mix a label with your target analyte, you don't want the zone to become really vertically broad, because that means that it becomes harder to detect, because per unit length, you've got less analyte. So you want to have a lot of mixing going in the XY plane. You don't want to have a lot of mixing going on along the Z direction. And a lot of these designs have been also optimized and looked at to get predominantly mixing across the channel, but not along the channel. The last one where I want to have a look at is actually putting little slants in the microchannel, because that's by far the easiest one to make. It also is least risky for any particles to block. And they also refer, some of these ones, that one is also referred to as a herringbone mixer. So here there's just slants in the channel where the liquid that's flowing across the slanted part gets bumped up, and that creates enough of a disturbance of the flow patterns that you get mixing. The herringbone here creates it in two different ways. So it's got a little angle on there, which means that it actually directs the majority of the flow to go up the wall, and you get a very nice circulatory profile of what the flow is doing. Again, creating that motion in the microchannel that you at high Reynolds numbers would already have because of convection. And here you're simulating that by creating a circulatory flow in your microchannel. As you can see, there have been a whole range of creative solutions to do mixing. Nice arrows, particularly hard just after lunch. So a picture on how it actually looks like when we're talking about a microchannel. So here you can see one of these herringbone mixers. You can see that we've got a long end and a short end. A fluorescent dye is coming in, and you can see it being pushed along and mixed around in the microchannel by having the structures on there. So that's the way that the herringbone mixers actually swirl the flows through the microchannel and achieve their mixing. If we then go for active mixing, again, the amount of solutions is as big as the creativity. Any way that you would be able to create any kind of flow disturbance, I think, has been tried. This is just a summary of 8 of them from a textbook. So you can get better mixing by just using your pump. If you get your pump to pulse strong pressure pulses, that already creates this disturbances that you could use for mixing. These pressure pulses could be coming not only through the inlet, but also having some pressure disturbing elements coming in from the sides, which could be a valve or just a little push of a liquid in there. Again, you create this disturbance of flow. This one already referred to, just have a little stir bar in there that starts whirling around whenever you got a flow. You get an in situ mixer. Applying an AC voltage, you get things to move left and right, either electroosmotically or just get the direct flow along with your analytes. Again, it nicely mixes the analytes. We get serial segmentation, which means that we get the slow and the fast route into those eddies going to the outside, and that enhances the mixing. We can use pulsed flows going in of one of the 2 solutes and the other one has to follow. We can create, that one's got an AC voltage applied to it as well. So we get changes in electromigration happening in the channel that help for our mixing. Plus H. That was H. H was a thermal effect. So if you have a laser absorbing dye in there and you irradiate it with a laser, or maybe some ion particles, they get hot. If you get hot, you change viscosity, which means that the viscosity of your 2 different solutes, 2 different solutions is not the same anymore. That difference in viscosity actually creates the circulatory flow as well. So by using thermal effects, you change viscosity, and by changing viscosity, you change the way that you destabilize the fluidic balance that's been established, which is the driving force behind a lot of these mixes. Active ways that were in there were the acoustic version that I just talked about, where you get a piezoelectric transducer, a little disc that you can see up there, and you can see that the microfluidic channel that is made in a material called PDMS or silicon rubber. Easy to make. We'll go through microfabrication in a little bit more detail later on. But if you've got a template, you can pretty much just mix the PDMS up in a 1:10 ratio. Make sure, put it in a vacuum to remove the bubbles. You cast it over, you put it an hour in the oven, and you've got a chip. So very easy to make. You can see that this PDMS device has got some ports going to the outsides that have sharp corners. And these corners, they focus the acoustic fields, and by that creates these vortices, maybe even with a little bubble. And these microstreaming edges actually help the solution that's flowing through the PDMS channel to mix. We've done it recently to try to get to homogenize some fresh fruit samples, and it works amazingly well. So you just only need a very short microchannel, put the acoustic field on, and the flow gets so much disturbed that you get over a very short channel length, you get very nice mixing. This was a nice one, and I heard that we had a lot of organic chemists in the room, and it's always good to see that chemistry can actually be able to play a physical role as well. In this instance, they've got a two reagents phase, but there is a third phase drawn here in the middle in blue dye. I got it. Thank you. Yeah, beautiful. Oh. That's nice.
I think we have to do this one. No.
Yeah, beautiful. We've got one spot now, not the whole world. So here you can see a narrow line, and what they've created was a surfactant, and it was not just a normal surfactant, it was a photoactivatable surfactant. So it wasn't a surfactant when starting, which meant that the two different oil phases and the aqueous phase didn't mix at all. But when they activated the surfactant with some UV light, it actually started working as a surfactant, meaning that the water and oil could mix. And these modules here were used as little mixing chambers. Light went off, the surfactant lost its surfactant properties again, which means that you can get back to the non-mixing phase. So that's a way where you can actually get actuation or mixing or a physical effect, having realized with having clever chemistry. I have no idea how they made it. I've even not looked up what the molecule looked like, but they had a surfactant with UV absorbing groups that rearranged itself upon irradiation with UV, and that allowed for nicely parallel flows unless there was light there, and as soon as light was there, the surfactant became active and water and oil became miscible and ended up in these chambers. So nice paper, particularly if you like contributing some of the chemistry elements. Another personal favorite of me, that because it's particularly mesmerizing to look at, are cilia. How many biologists did we have in the room? All our biologists have left. Cilia are the little wavy things that sit in your gut and in your nose and things. So they're the little sea anemone-like structures that wave around and transport snot and all other stuff in your body fluids. A lot of our fluidic systems in our body are actually driven by these cilia. Most gross fluids are. But yeah, they are little pillar-like cells that have an active motion and wave along. And microfluidics people wouldn't be microfluidics people if they didn't think like, can we make them as well? And yes, of course, they're beautiful mixers. So here you can see a microchannel, nowhere near as bad to look at as the inside of a gut. Nicely lined up pillars in here. You can see a little higher magnification here. And by making these pillars from a magnetic material, you can actually get them to swirl around. So you can see here this one making the motion, and you can see get all these pillars with a magnet to just happily form their little figure eights. And here you can see without the cilia activated, we've got laminar flow. We don't have a lot of mixing. Here we get the cilia to do their little swingy thing, and we get beautiful mixing. So at that point, we get an active element that we can activate using an external magnet, and we get the cilia to work. After that, people got creative and realized that there was a whole range of different ways that you could actually get these cilia to move. So we just looked at ones that were magnetically actuated. And if you activate the magnet, you can get the cilia to bind over, and that's how you get them to mix. They're also for our organic chemists that are always making the most wonderful molecules. You can get molecules that change the way that they interact together when you irradiate them with light. So they may go from a stiffer version to a less stiffer version. If you get that conversion to take place on the cilia, then you can actually get it to bend over and straighten up again, depending on irradiating. Again, beautiful mixer. You can do it electrically if you make your cilia from a conducting material, polymer electrode, for example. You apply charge, you get some repulsions, and you can get the cilia to move away. You can also actuate them pneumatically. If you make them hollow and you make them like a little inflatable balloon, if they don't have anything in there, they lay sad on the surface. And if you inflate them, you can get them to stand up straight. So you can use pneumatic actuation to get the little stirrer bars in your microchannel to stand up, which is a very elegant way of mixing, typically used in a little bit larger volume. So they typically, with the silica, they use 200, 300, 400 micron channel deep and not the 20 micron deep ones, because you probably need some length to actually get a proper bend out of them. But the nice thing for people doing cell culture is that it's a really mild way of mixing. So if you've got sensitive cells to shear stress, you can actually, in a very gentle way, stir the solution around where you don't cause a lot of stress. And that's advantageous for a lot of biological systems. So to finish this part on mixing, laminar flow can be great if we want to have controlled extraction, removal of a component using things like an H filter, but the absence of convective mixing can be a bit of a pain. Luckily, we've got a very wide toolkit of different mixes that we've got available. We've got active mixers that need a source on the outside, which could be an electric field, AC or DC, could be a heater, could be acoustic, could be anything you can dream of. Or it can be done passively using the fluidic structure by either putting the slants on the bottom or getting split and recombine mixers, getting these sharp turns to create all kinds of eddies. So there's different ways that you can do with your microchannel to achieve mixing. There's different elements that you can put to the outside of your microchannel to achieve mixing without having to change the geometry and keep your fabrication simple. Whatever is best for your application, it's up to you to decide, and maybe it doesn't even matter if it gets you from A to D. So that's the bit on mixing. Are there any questions on mixing, or ready to go? Done the fundamentals there. So I'll need to change my slide set. Chat amongst yourself for 2 or 3 minutes. I'll load the next set where we'll go through a couple of applications, and then we're done for the day. It's already 3:30. Any questions here yet? And let's get through some examples and then get home and relax, because I reckon I've probably overwhelmed your poor brains with a lot of information of things that you didn't even know were a problem. This session is going to be a little bit more sit back and relax. I put together a couple of different examples pulled from left, right, and center of microfluidic systems that are somehow having something cool to look at. And the cool could be in the microfabrication, it could be in the application, it could be on where it's used. Couldn't cover all the cool things in the world, but just see this as a little bit of a breathe and relax session. We've had a pretty tough day with a lot of equations. This is where it finally all is used for. And this morning with the opening sessions, I said, think big, think about all the big problems there are. I hope there's some of big problems in these slides that actually trigger your interest. So one of the things that I just think is really, really cool, how much you can do in a very small space, has been done for probably 10 years or so, maybe even longer, by Amy Hurst group in Berkeley. Big group, really, really strong research, really smart. Have a look on the website. It's always in absolutely great order. But they do really nice, significant work on doing high throughput proteomics work. The concept of what they've done, what I really like here, and I realize we'll only do electrophoresis later this week, so bear with me if electrophoresis is not your stronghold yet. But what they've done is in very high throughput. So the impressive part comes later, but you need to understand this to appreciate. They've got structured microwells that are about 50%. The scale bar here is 100 micron, which means that that microwell there is probably in the order of 50 micron. About half a hair in diameter, so very, very small hole that they can put a little cell in. They can then add a lysis agent, which they, if you're not a biologist, you think about a cell. A cell is a big blob that's got the nucleus sitting in there. You can selectively lyse the outside of a cell, so you get the contents of the cell, leaving the nucleus intact. And then there's other agents that are a bit more aggressive that also lyse that nucleus. And that's exactly what they've done here. So first they add a lysis agent that only lyses the cell wall. So this little cell that was happily sitting in its little hole gets soap on it and all other kind of stuff to disintegrate. And the nucleus stays intact, but all the normal proteins that are present in the cytoplasm, they sit in that little well. They apply a potential difference, which means that the negatively charged proteins will move this way. Then they add a second lysing agent that lyses the wall of the nucleus. They put the field in the other direction. So we already have the cells that have the protein bands in the gel electrophoresis that have come to this side. They apply the field in the other direction, and the cells the proteins that have come out of the nucleus migrate the other way. So we now have 2 bits of gel electrophoresis. One is coming from the cytoplasmic proteins. One of them is coming from the nuclear proteins. You can add, like you do normally in blotting, you can add antibodies and put probes in there to make them, to visualize them. So here we can see the little circle where the cell with the different dyes is visualized in the microwell. After first step, you can see there's a protein called turbo GFP. That's probably not even colored, but it's fluorescent by itself. It's migrated. And here, and I hope that you can just see it from where you're sitting, there's a tiny little blue blob there where it's the arrow points at laminin, so which is a nuclear protein. So you can see you can do protein gel electrophoresis from a single cell, from the cytoplasm and the nucleus on a tiny, tiny gel, which is where this picture comes in. And this is where I hope that it's kind of expressing, getting your interest. This is a normal microscope slide. Normal 5 by 7.5 centimeter. This square is increased in here, and this is an array of all these functional units. So all these blits where we've got the green blob and the pink blob are all gel electrophoresis systems. So those of you that have ever run a gel lab, you know these slab gels, they're big things. They're a lot of work to make, you can't get a lot of throughput. These are hundreds of these, because this in here is, the scale bar is 1 millimeter. So this is a small section from the microwell. You can see how many gel electrophoresis assays they can do. And if you realize that these all can be done on a single cell level, it actually allows you for individual comparison of individual protein levels of a single cell population. Because here you can see there is, on this microscope slide, there are 2,000 different wells where with an electrode interface, you can, on individual cells, do lysis and Western blotting at the same time. So that creates a very different amount of data than you can get with the normal slab gel that you cast from a comb. Plus you can get individual information, because getting numbers from 2,000 wells at a time allows you to understand a lot more about what the variability is within your different cell population than when you would be analyzing a mixture of 2,000 cells in one tube, because then you just get the average, but you don't have any idea how that average has gotten together. So really, really cool work. Very nice fabrication methods, really nice way of bringing gel electrophoresis to the absolute maximum in terms of throughput. My other favorite, lab on a sheet. It's a fairly old paper, but I really like the gesture of what they're doing. And those doing pharmacology like probably the fact that you can do some pharmacology studies on that as well. So this is a small dialysis probe that can be implanted into a sheep, and a box that's been built to be rugged enough to do electrophoresis on the back of the sheep. So the dialysis probe goes into the veins of the sheep. It's mounted on its back. Then the dialysis probe, here it sits in a vial. In the experiments, it's set in the sheep. Collects small molecules from the sheep without injuring the sheep itself at all. The sheep probably only thinks it's got an annoying backpack on. Then the dialysate from the sheep ends up being injected into the chip. Here we've got a nice device where we're playing with the difference in hydrodynamic resistance. So normally we've got a very big channel in there with low hydrodynamic resistance where our dialysate coming from the sheep is being pumped through. Sometimes we can apply an electric field to get an injection of a small plug into our electrophoresis system. Don't worry about how we get that done. We'll have a special session on how we inject in capillary electrophoresis later this week. But what we can do is inject a small sample zone into the separation channel here, where it can be separated into its individual components. To make it even better, there's an electrochemical detector integrated on board, so we don't need any light sources. But we've got an electrochemical detector sitting here in the end. And if we give the sheep a little shot of nitroglycerin, we can actually measure the nitrate coming up because that's electrochemical active. So here we can see the time that the instrument has been sitting on the sheep's back, no nitrate levels being measured at all, up to about 110 minutes. And then you can see every couple of minutes a CE analysis is being done, and we can detect the nitrate in the sheep. And as you can see, the sheep was unharmed. The CE instrument by the end of the day was not, unfortunately. They took the instrument off the sheep and left it in the paddock, and the sheep walked over it. So this was a one-day experiment, and they then had to rebuild the system because the sheep destroyed it after the first day of testing. That was not in paper. I heard that later, but I thought it was pretty funny. But yeah, that's a kind of thing. If you get your micro-analysis system small enough, you can actually put it on patients, or in this term, on people. Different gear, going to Greenland. Greenland is that bit of ice that's not Antarctica, that's close to Australia, but the other side around. There is the Alexander Beaton. This is working somewhere in the UK, I forgot where, I think Southampton. And they're doing really great work where they are taking environmental monitoring really seriously and want to bring the analytical systems for advanced environmental monitoring into the fields, including Iceland. One of the things I like for this is that we've got all these great things in the microfluidic toolbox. Sampling world-to-chip interfacing is still a big challenge. And here they've just decided to give up and not make life too difficult and just have a normal 0.45 micron syringe filter sitting in the tube. Then their analytical system is flow injection analysis, where they've got a reaction taking place that gives a colored reagent. And then they've got a little photodiode there to measure the color. So analytical assay, not really advanced. Flow injection analysis, for those of you that have done any chemistry, is not probably going to get a Nobel Prize again in a hurry. Very simple sampling system, but they took it to Greenland. So here we've got a rock where they've got the analytical system sitting. Here they've got in a glacial stream. So there's the system sitting with some reagents sitting in bags, and the data logger was sitting there on the rock. So system got taken out into the field. This is truly doing analysis in the field. You hear me just talking a little bit unfriendly about a very simple benign system. Fluidically, that's what it looks like. So that already tells you, if you translate a normal benchtop system to microfluidic, you actually do make life complex quite quickly, because this system had to do everything. It had to be able to calibrate itself, do a reaction where they converted the nitrate that they were after into nitrite. So they needed to have a cadmium column to do that. Liquids needed to be pumped and valved into different directions. So this part in here is the fluidic control. So all the crosses are valves, and there is 3 different syringe pumps to drive the different fluids on the system. This is how the microfluidic system looks like. With different channels, we can see here that this is a mixer. So they've decided that they didn't need any active elements in there, but a long channel was good enough to mix the grease reagents with the nitrate. Here another mixer for the standard. You can see the grease reagent sits here. Column in and column out are going to the cadmium column for the conversion of NO3 into NO2, because the grease reagent only measures NO2. So that's kind of the visibility of the assay that they wanted to measure. Hydrochloric acid, because it needed to be done under acidic conditions, buffer to keep the pH. That's where the sample came in. Need to have water in there as well to have a blank signal. Couple of different standards to do the calibration. And of course, you create every run, you need to create a bit of waste. You don't want to have that just ending up somewhere in Greenland. So you need to have a waste bag as well. Relatively simple system, seems to be, but at the point you need to have your calibration, your blank, your sample coming in, some colorimetric reaction taking place. It actually gets still quite complex. But they did a couple of deployments. Here is a very similar system where they put it somewhere in a river. But I like this paper because they actually put a system here where we've got the stepper motor driving the different syringe pumps. There's the electronics that are operating it all. There's a whole assembly of valves. And if you look at it, some solenoid valves, they're only that big, but by the time you need 5 or 6, you actually get to a fair footprint in the instrument. And somewhere here in this big block of engineering, we've got a microfluidic system where in the micro channels, the chemistry takes place. So lots of engineering, very little chemistry taking place here. But from an environmental perspective, one of the nice things that they reported in this paper is that they found some day-night variations in some of the analytes. I think it was phosphate they're looking at here, that no one had looked at before, because no one had ever been able to sample at the intervals they were able to do automatically to actually see that day-night variation in levels that they then link to photosynthetic activity. So really cool new data for environmental scientists that could come out from a little bit of chemistry and a lot of engineering. Very different gear, exosomes. Anyone heard of exosomes? Biologists, biotechnologies in the background. We have heard, you must have heard of an exosome. So exosomes are little blobs, little vesicles that different cells separate away. There's some concepts that think that exosomes are very important in cell-to-cell messaging. Cancer biomarkers are present in exosomes as well. So they are cell-like structures, little blobs, but they don't have a nucleus. They're not independently moving, but they're out in your circulation. So they're floating around in your blood, even though most of you, all of you, didn't know about the existence. You all are full of exosomes. And exosomes are significant biomarkers, and particularly tumors secrete different exosomes from other cells. So if you want to know if you've got cancer, rather than searching and scanning your whole body in the hope that you don't find something, or that you do find it if it is there, you can actually also pick up that you've got the wrong exosomes in your circulation from only what they call liquid biopsy, which is just some body fluid, so quite possibly just some blood. So this in here is, if we compare it to the previous microfluidic device, this is actually not that hard. We can kind of well understand what's happening. We've got 2 inlets here. One of the inlets we get some exosomes, or no, some magnetic beads that we mix with a blood mixture that contains a lot of different things, including exosomes. Our magnetic beads, as you can see, for the non-biologists here, these weird Ys are antibodies. And antibodies are biorecognition elements that whenever they think they know it, they grab it and they hold on. So they're little grabbing arms. And these were our special CD63 antibodies. And they really like to grab a recognition element that sits on some of the nasty exosomes, which is called CD63. There's probably a good reason behind that name. So these little grabbing elements find a dirty blood sample, find the exosomes. So we've got our magnetic beads come in, our exosomes come in, happily mixed together. Then we've got the first chamber here where our magnetic beads are being halted because we put a magnet underneath. This magnetic bead says, hey, magnet, I want to be here. I don't want to flow anywhere. So can flow on. We can put some buffer through inlet 3 to wash away anything that we don't want to have. Anything we do want to have stays on our magnetic beads, stays sitting there. Then we put a detection antibody into inlet 3. So we remove the washing buffer that we had. We add the reagent with the next antibody, and we get it to go through this structure. Why do we have another zigzaggy thing? What were we doing there? We just spoke a whole hour about mixing. Remember? Me talking, mixing, swirly-whirlies, serpentines. Second serpentine there, again mixing. So add two reagents together, mix, mix, wash, new reagent, mix, mix, repeat of the same functional unit, wash, retain it in chamber, and then go to the outlet. And I think I had on the next one. So what they did was in this chamber, having a detection antibody, so antibodies nicely stacked together. People doing all kinds of biological assays really like you stick one antibody to it to know it's there, and then you stick the other antibody that gives light or gives fluorescence to the first antibody you put in. They call it a sandwich assay, and it gives usually typically a pretty red or green color whenever you look under a microscope. So with a microscope, you could see how many of exosomes that were nasty your beads actually captured, and then I could collect them in an outlet for some transmission TM analysis as well to look at the morphological characteristics. I'm not an exosome person, so I would have no idea how a cancerous exosome would look like, but I like the microfluidic structure. And again, liquid biopsies, getting quick diagnostic markers. This chip is not that complex and really, really useful in fishing out the things that you want to look at from the big complex soup that blood could be. Exosomes are popular. So another exosome example here that is kind of similar, adding different reagents, but then rather than having different channels mix together, they used pneumatic valves here. So they used a flexible material where they could create some valves by inflating some artificial balloons. So the thing that's called valve there is pretty much a balloon that gets inflated. The balloon is inflated, liquid can't get through, it's closed. Balloon gets deflated, it's open again. Other than that, it's fairly much the same thing where we've got a blood sample, we've got the magnetic beads that are probably the same ones that were used in the other one. We've got a washing buffer, and we've got, in this case, a substrate that allows for a coulometric reaction. And here you can see we've got need another fluidic layer there. We've got our reaction chamber sitting here, and then we have our pneumatic valve sitting into the other layer, so we can actually squeeze the channels down. But yeah, that's another example where exosomes are nice to look at. Cancer detection as such is an area that gets a lot of research funding and therefore can be a very cool application. So here we've got a membrane-based device that uses surface-enhanced Raman spectroscopy. So those of you that are into the fundamental analytical detections in the spectroscopy, the sample preparation for that can be done with microfluidics as well. So what we have here is first a membrane integrated device where we can do some dialysis to get our target proteins separated away from the rest of the sample. So we have a membrane-based device to do some sample preparation. And then we've got from memory some posts to do Raman spectroscopy on. So yeah, here we've got the layout where we've got our fluidic system and our dialysis membrane sitting in there. so that only the target proteins and things that are smaller than that can get through. And then we have some interesting nanotechnology going on, where we've got these tiny pillars that get coated with, I think it was silver. Yeah, gold. Oh, silver nanograins. So we got some silver nanograins that get coated onto these little pellets, and that then can act as a substrate. So we've got this big now microfluidic device with all the used channels where we can get the sample in that may contain a protein for breast cancer. Breast cancer can get through the membrane and find its way through this pillar. By having these gold nanograins on that, gold nanoparticles, we can do surface enhanced Raman spectroscopy, which means that we can identify these proteins if they've stuck to the pillars or not. And here you can see the different source spectra, where you can see if we've got a protein and albumin presence, we get a Raman spectra that looks like an absolute mess, and we can't really see P is the protein that we're after. We can't really see the peak of the protein that we're after anymore, because all the albumin in the blood sample is just masking it all. But by adding a simple dialysis step, we can actually see the peak for the Raman characteristic peak for our target analyte for breast cancer. We can distinguish that doing Raman spectroscopy on these tiny little silver nanoparticle coated particles. So here the nice thing is probably where you can use the microfluidic sample preparation to deposit your substrate onto these tiny pillars, that then after evaporation of all the liquids, the protein concentrates itself. You can do spectroscopy, and you don't need to have a huge sample volume to still get good data on what the protein is that is or isn't present. Next part that I thought was be good to mention today before we're going home is that a lot of the microfluidics is happening on paper as well. And you can combine paper with different technologies. So paper is nice because paper likes to absorb water. So there's paper towel that you may use to clean up a spill in the lab. You can put hydrophobic barriers, and we'll go through another session later, to direct flows in certain directions on a bit of paper. And here they've very cleverly combined a paper fluidic device with a patch that contains a whole range of microneedles. The microneedles take a small liquid biopsy that then gets assayed, and we get probably an immunoassay happening here, where we can see a certain bioreaction having taken. So we can do diagnostics on a bit of paper with having very small needles. They don't need a nurse, but you can just put on your skin, a little bit of bloody fluid is taken, and you can do a point of need analysis on the paper fluidic device. This one was really nice because it's showing you how you can have a very simple device to still mix and do DNA amplification. What they've got is little carbon rods here. So they fill reagents in the chip. Rather than having any active elements in there, they physically pick out the little rod, the little pin, to allow fluids to come into different contact. And that way they can get a sample in. Then they can add a solution to amplify the DNA. Then they add the CRISPR-Cas12, which is a way to visually detect amplification products. And by just first opening this one, then so getting the target DNA in, removing one pin to ask the reagents for the amplification, heat it up to do amplification, then pull the plug to get the CRISPR reagents in. And then if you had a positive, you got a nice green color. I think this is one of the last ones. So this is a nice illustration. I've already talked about acoustic mixing. Acoustic fluidics can be used for focusing as well. So here we've got red blood cells from a blood sample and bacteria. The acoustic field has been tuned so that the large red blood cells actually sit at a node here. The bacteria have got no idea what's going on. They're too small, which means that we can get all the blood cells separated out here in the middle, go to the waste, and we can collect the bacteria later on, and then quantify the bacteria, which is very important for our last application we'll be talking about, which is the diagnosis of sepsis. So sepsis is an uncontrolled response of the immune system in case there's an inflammation going on. And it is the most significant cause of death across the world, because it is very hard, partially because it's very hard to pick up. So if you go for a culture-based system, you're talking on average 15 hours of cell culture. Typically a patient is dead after 4. So analytical results come from a sepsis patient typically come too late. There are faster systems than the culture systems on the market. And this is a microfluidic system where they had a 30-minute sample preparation and then a PCR that was 75 minutes, but could be made faster in the future. So they used that acoustic separation that we just looked at the 3D image for. So all the red blood cells can go to waste. The bacteria could be collected. The sample that was then moved to a concentrating system where they, in the acoustic field, bacteria don't really nicely concentrate. So they introduced some particles that bacteria stuck to that do respond to the acoustic field to concentrate the bacteria. And then they could send the bacteria with that clump of particles to the PCR chip to amplify. So this is showing that with colored bacteria that acoustic focusing of the bacteria really worked nicely. And you can see here that they could diagnose sepsis patients with PCR. For those of you that haven't done PCR a lot, it's an exponential amplification of DNA products. You don't see anything for a very long time, but every time that it's amplified, you get exponential growth. Usually, if there is more than 40 cycles before you see any response, we say there's nothing there. It could have been a contamination. The earlier we can see amplification products, the more of the DNA was there present. The level at what this ends up is not really significant. So the important part, a measure for the concentration of DNA, is how early this midpoint comes. And the other thing that it needs to do is amplification needs to come over the threshold. So that's the way you detect these amplification strategies. The important thing here is that they could see their amplification of their product after their acoustic separation come up before the threshold point, which means that they got enough bacteria out to diagnose sepsis and what bacteria caused the sepsis, and therefore start timely treatments. And this in here is another fully integrated system where they immobilize the reagents. That's why I put that one in. So what they did in this device is compartmentalize the liquid to have separate droplets that all form their own little reactor. Each little reactor had a dried-in reagent plug that allowed for the amplification. So a drop of blood was introduced here. There was a vacuum-driven system to distribute the drop into all these little reservoirs. Before using the hydrodynamic resistance and the fact that the red blood cells were way too big, a very narrow channel on top siphoned only the plasma and not the blood into the detection cells. And they had a little plug there of the reagent to start the amplification sitting in there, and could vacate some of the chambers to create fluidic control. So they started off with empty channels, filling them with the amplification initiator, which is the magnesium that's required for amplification. They pumped the little side channels, they filled it up. They then removed the liquid and allowed it for a little bit to dry in. So there was a little bit of the cake of the magnesium chloride patterned onto the microfluidic substrate. That was done before the sample was introduced. So that was just sitting there as a reagent in case it was ever hit by sample. Then here you can see the formation where you see the liquid evaporating and therefore the spot to become increasingly bright. Here you can see the little reservoirs, how the little droplets, so these are the small sample volumes that were all being measured. The whole chip was being put on a heater to do RPA amplification. That all got activated by dissolution of this little reaction plug. All these little chambers did their separate amplification. So for all these small volumes, we knew if our target DNA was present or not. And then here you can see, or you can probably hardly see, you can see the little green dots here where the target DNA was present. If it wasn't present, then that meant no amplification products. So here you can see that the sample got compartmentalized on all the different areas, and you can do a massively parallel amplification on very small volumes, which provides you with another means of quantifying the target DNA if that's present or not. So that's where the amplification happens. So that's where the blood cells stayed behind, plasma goes there, and then the stained amplification product, it does various. That's the one that I just got through, and here you see an example of where that's used for a real sample, where you can see that some of them had the target DNA and some of them didn't, which again, you simply start counting the bright green and the non-bright green dots to quantify your amount of amplification product. I think we are done for getting, well, you can also use it for antibiotic susceptibility testing, but I think we're all getting fairly tired, so feel free to look up that paper. It's another important amplification. You are in antibiotic susceptibility testing, or you're just happy to go home? Honest to be either way. It's a nice paper, but I think we all have had a very long day. So the conclusion from the couple of slides that I showed you is there's a tremendous amount of progress that's already been made in the area of microfluidics. There's a lot of work that's been done. But after a period where people were probably saying, oh, microfluidics, why do you have to do it? We're actually at the uphill battle where we know that we've got a great toolbox, but we also know there's a lot that we don't know, and there's a lot of problems that we still need to be solved. A lot of innovations that keep on coming in from other fields also still can be adopted by microfluidics. Most significant, we can see that in DNA amplification, while PCR used to be golden standard, the RPA, LAMP, isothermal amplification techniques have taken over. And there's new techniques in the pipeline all the time that are all probably going to be more robust, faster, more amplification products, easier to read out, a whole range of examples like that. So there's always new opportunities, developments in new fields that are yet to be adopted by the microfluidic community. But what is important to know is a lot of work has already been done. Andreas had his idea of the microtest system in '89. There have been a lot of people working since '89 trying to develop microfluidic systems for whatever you can dream of. Make sure you do a good literature research, A, to get inspiration, B, to find out where the bottlenecks are and what the problem is that you're actually trying to solve, because it's good to have, if you're having a very applied project, you may just get an off-the-shelf solution out from the literature. If you've got a really new problem, it may really help to understand where other people got stuck in literature developing their essays and find inspiration how you could do it smarter. Because one of the things that starts becoming clear is just translating the workflow on what you used to do in the lab on the benchtop is probably not the way to go, because it gets too complex, and simplicity is the key to get a robust system where you can produce 2,000 and have 2,000 working and have 2,000 happy customers. Because by the end of the day, a lot of this is driven by the dream of people to get a commercial system out into the community. And you've seen it, we get a COVID outbreak. We've got great microfluidic technology, but it is the good old lateral flow test that by the end of the day, it isn't really accurate, it's not really precise, but the whole world has relied on it because it's easy to use, it's fast, and it's reliable. So have a look at what's in the literature, but we are definitely in a good place where, unlike here where nothing was known and people thought things were great and they were then getting disappointed later on, we actually do understand a lot more at the moment, and there's great opportunities to develop great applications, and I continue to be convinced we'll have a lot of microfluidic systems out into the future. So I hope you've enjoyed today. Tomorrow will be a lot more separation sciencey. We'll go through different days. If something doesn't float your boat, it's all part of the microfluidic systems, and there's physics elements, there is analytical elements, there's microfluidication elements, there's a lot going on. You can never love it all. So just, if you don't like a day, get it to flow over you and find a collaborator that takes care of that part if you end up working in the area. That's a good thing of having other people that to work with. They all like different things, and that means that you can not do the things that you don't like. Thank you very much for being here today, and I'm looking forward to seeing you all tomorrow again.